Alors, bonjour tout le monde, bienvenue à ces deuxièmes portes ouvertes de l'espace IBM Quantique de l'Institut Quantique. On est très content aujourd'hui de vous avoir parmi nous. Mon nom est Justin Lefebvre, je suis responsable, oui, des partenariats à l'Institut Quantique et aussi, évidemment, très impliqué à l'intérieur de l'espace IBM Quantique. Si vous nous écoutez et que vous parlez français, quand les présentations seront en anglais, vous avez un bouton d'interprétation pour une traduction simultanée que vous pouvez trouver là, dans votre écran. Je vais parler anglais pour dire une bienvenue aux anglophones qui sont parmi nous et je vous reviens en français dans un instant. Hi everyone, I'm happy to welcome you to this second open house of IBM Quantum Hub in Sherbrooke. We are happy to have you with us today. We had a great year since last year. We are pretty happy to present you what happened in this last year with various partners, various students, researchers that will be with us today. The presentation will be in both French and English, and I will host part of the presentation in French. If you want to listen to a simultaneous translation, you can click the right button. Well, somewhere in your screen, you should find it pretty easily and have this translation live. Alors, je reviens en français pour les prochaines minutes et je vais probablement me promener comme ça là, au cours de l'animation en anglais et en français. Donc, porte ouverte de l'Institut Quantique, pas de l'Institut Quantique, mais de l'espace IBM Quantique de l'IQ. Laissez-moi vous présenter l'équipe. Je vous disais que je travaille dans ce hub de programmation, l'espace IBM Quantique. Mais évidemment, je ne le fais pas tout seul, avec toute une équipe autour qui travaille extrêmement fort. Et laissez-moi vous présenter nos deux dernières recrues qui se sont joints à nous dans la dernière année. Donc, Sarah Blanchette, Marco Armenta, qui sont avec nous. Sarah, vous aurez d'ailleurs l'occasion de l'entendre un peu plus tard ce matin. On a aussi Aiki Rasolomanana qui était avec nous comme stagiaire cet été, qui va venir aussi vous présenter son expérience de stagiaire à l'espace IBM Quantique. Et bon, en bas à droite, vous avez l'équipe qui était là l'an dernier. Donc, je vous représente Tom Mala, qui est à l'animation des communautés, Jean-Frédéric Laprade et Maxime Dion, également programmeur à l'espace IBM Quantique. Alors, espace IBM Q, IBM Quantique de l'IQ, qu'est-ce que c'est? Bon, évidemment, c'est un hub de programmation quantique et qui dit hub de programmation quantique, dit entreprise qui participe à la vie de ce hub-là. Et on est très content ce matin de vous annoncer l'arrivée d'un nouveau membre à l'espace IBM Q, nouveau membre qui s'est joint à nous dans les derniers mois, donc Lockheed Martin, et vous aurez d'ailleurs la chance d'entendre un peu plus tard ce matin Danny Cougar de Lockheed Martin venir parler des projets de recherche en info quantique qui se passent de leur côté, de leur intérêt évidemment à devenir membre du hub, mais aussi à travailler sur des projets de recherche collaboratifs avec nos chercheurs ici à l'IQ. Donc, on les entendra un peu plus tard ce matin. On a évidemment un autre membre que vous avez rencontré l'an dernier si vous y étiez, c'est CMC Microsystèmes. Donc, Hudson Mendes qui sera avec nous également ce matin pour nous parler de la recherche du côté de CMC Microsystèmes et de l'intérêt grandissant, en fait, de leurs partenaires là, pour les différents projets d'informatique quantique. Maintenant, je vous rappelle, l'espace IBM Quantique, comment on l'a travaillé depuis 1 an et demi. Donc, on est content du chemin qui a été parcouru en 1 an et demi. Puis, vous allez voir plusieurs évolutions. Si vous étiez là l'an passé, vous allez voir qu'il y a vraiment plusieurs éléments qui ont muté au cours de l'année. Donc, on a évolué, on a fait plusieurs projets de recherche, on a établi plusieurs partenariats. C'est ce qu'on veut vous présenter ce matin, donc vraiment avec une communauté riche qui est autour de nous. Mais ce qui n'a pas changé, je peux vous dire, c'est cette image-là qu'on avait l'an passé, qui est encore là cette année, qui reste les fondements, dans le fond, du développement de l'espace IBM Q. Donc, la recherche qui est fondamentale, qui est centrale, on veut comprendre l'info quantique, on veut développer des algorithmes, on veut développer des applications qui nous donneront éventuellement un avantage quantique, mais on veut comprendre, on veut former les gens. Donc, il y a vraiment une question de recherche et tout de suite, je viens de dire formation, on veut développer l'expertise, donc la compréhension et il y a tout un élément de formation qui est extrêmement important et qui sera également le part de l'avant-midi ce matin. Donc, comment on va chercher ce développement de l'expertise-là, autant ici à l'Institut Quantique que chez nos partenaires. Donc, comment on forme les différentes équipes qui travaillent sur les projets. Donc, ça fait partie vraiment là, des fondements de l'espace IBM Q. Et il y a toute une notion de communauté, d'écosystème. Donc, comment on bâtit cette communauté de chercheurs, d'entreprises, d'étudiants, de professeurs qui travaillent avec cet objectif de développer la compréhension de l'info quantique. Donc, notion de communauté est extrêmement importante et je vous dirais que les portes ouvertes auxquelles vous assistez ce matin s'inscrivent bien dans cette notion de communauté, de dynamisme d'écosystème. Donc, ce matin, vous aurez des présentations du côté recherche également de Stefanos Kourtis, qui est directeur de la plateforme de calcul quantique ici à l'Institut. Donc, l'espace IBM Quantique fait partie de la plateforme. Donc, vous entendrez Stefanos vous parler de la recherche que lui fait comme chercheur. Donc, comment il utilise l'info quantique de son côté avec son groupe là, pour avancer les connaissances, avancer la science. Vous aurez également Avec, je vous le disais, là, qui va vous parler donc plus du côté formation de son expérience ici à l'espace IBM Q l'été dernier. Puis aussi, côté recherche, vous aurez Statistique Canada avec qui on a eu un super beau projet collaboratif. Donc, Zachary va venir vous présenter comment Statistique Canada s'est intéressé à l'informatique quantique et comment avec eux, on a développé un projet de recherche conjoint sur lequel on a travaillé et évidemment dans le meilleur intérêt de nos deux organisations. Donc, ça va être intéressant de l'entendre, voir comment ça s'est vécu du côté de Statistique Canada, ce processus-là. Donc, voilà pour je vous dirais, ce qui s'en vient. Évidemment, on aura également des gens de chez IBM qui viendront nous présenter donc où en est la technologie, où en est là, donc l'avancée de leur roadmap là, qu'ils nous ont présenté l'an dernier. Maintenant, on veut savoir comment ça avance et où est-ce qu'on se situe dans les prochaines avancées qu'on devrait observer. Quand on parle de projet collaboratif, il y a un roadmap, un plan de match qu'on propose aux entreprises. Je vous le présente rapidement. Donc, en 7 étapes, l'idée, c'est de voir avec nos partenaires où ils sont rendus. Est-ce qu'ils sont déjà intégrés? Est-ce qu'ils ont déjà intégré une portion de quantique dans leurs activités ou est-ce que c'est vraiment le début? Est-ce qu'ils ont des équipes dédiées? Est-ce qu'ils sont capables? Est-ce qu'ils ont des gens qui sont peut-être pas des gens en quantique, mais qui voudraient, qui auraient la possibilité de développer leurs connaissances de ce côté-là. Donc, il y a un tour d'horizon à faire avec les partenaires. Ensuite de ça, créer une équipe de travail, trouver des sujets potentiels, donc d'application. Évidemment aussi, il n'y a pas encore de retour sur investissement en info quantique, mais l'idée, c'est stratégique. On veut positionner stratégiquement nos partenaires, on veut positionner stratégiquement les projets qu'on fait dans l'avancée des connaissances, encore une fois, autant chez les partenaires que nous ici à l'Institut. Donc, comment on fait ça ensemble? Bien, vous avez sous les yeux le plan de match proposé et comment ça va se décliner par la suite. En fait, il y a une offre de service. C'est l'offre de service qu'on a développée au cours de l'année. Donc, celle-là, en fait, c'est raffiné, je vous dirais, au cours de la dernière année. La première portion ici, là, les 4 premières lignes, on est vraiment pour les entreprises qui ont probablement peu ou pas de connaissances en quantique déjà, puis de voir un peu comment on fait pour se lancer. C'est quoi les premières étapes pour travailler ensemble vers des projets collaboratifs? Puis éventuellement, la portion membres, donc on parle d'entreprises, comme CMC Microsystèmes, comme Lockheed Martin, qui ont déjà un bon bagage en quantique et qui désirent donc accéder aux systèmes les plus avancés d'IBM. Donc, aujourd'hui, jusqu'à 127 qubits, on va en entendre parler dans quelques instants. Donc, un nouveau processeur quantique de 127 qubits qui vient d'être annoncé la semaine dernière. Peut-être que je viens de scooper là, ce qu'IBM va nous annoncer, mais bon, vous l'avez probablement vu dans les médias déjà. Donc, et évidemment, pour les membres, il y a plusieurs niveaux où on est capable d'intervenir avec chacun. Donc, est-ce que c'est l'accès en plus de projets de recherche? recherche. On pourrait même penser éventuellement donc d'un membership, mais plus une chaire de recherche en info quantique. Donc, plusieurs niveaux encore là d'implication puis de travail qu'on peut faire ensemble là, du côté de l'espace IBM Q. Donc, ça vous donne un peu le survol de l'offre de service côté projet collaboratif. Maintenant, je vous disais que la communauté est extrêmement importante et la formation également. Pour vous donner un survol depuis le démarrage de l'espace IBM Q le 1er juin 2020, avec l'équipe, on a donné plus de 75 webinaires et ateliers et c'est plus de 5000 personnes qui ont assisté à ces 75 webinaires-là. Sarah va vous en parler un peu de ce qu'on a fait, entre autres, du côté des cégeps, autant à l'automne 2020 que cet automne. Donc, encore là, il y a eu beaucoup de bruit dans plusieurs cégeps de la province. Donc, vous en aurez un aperçu de ce côté-là. Mais je peux vous dire que c'est plus large que ça encore. Donc, on a parlé avec des entreprises, des fonctionnaires fédéraux, des fonctionnaires provinciaux. On a parlé avec, évidemment, des étudiants universitaires, des étudiants au bac gradués. Donc, la foule à qui on s'est adressé dans ces 75 ateliers-là est extrêmement variée. Vous avez ici le nombre de curieux quantiques. Donc, si vous n'êtes pas déjà abonné à l'infolettre, vous pouvez le faire dès maintenant. On peut mettre le lien dans le chat si vous êtes intéressé à vous abonner pour recevoir toutes nos nouvelles. Si, évidemment, vous ne l'êtes pas déjà, donc vous voyez que vous êtes de plus en plus nombreux à suivre Curieux Quantique. Et pour les entreprises et les organismes partenaires, une autre nouveauté, c'est l'offre d'ateliers. Donc, je vous disais, on a monté des ateliers tout au cours de l'année. Voici l'offre d'ateliers. Pour l'instant, on en a 6 qui ont été montés. Donc, 3 d'introduction, 3 qui sont de catégorie intermédiaire. Donc, si vous êtes intéressé à en apprendre plus, à aller plus loin, vous pouvez me contacter. Donc, on peut parler de projets collaboratifs ensemble, mais aussi on peut parler de formation avec ces ateliers-là. Et nos programmeurs et programmeuses donc, vont se faire un plaisir là, de venir vous présenter les ateliers s'il y a un besoin là, du côté de votre organisation. Donc, c'était le survol très rapide de la dernière année que je voulais faire avec vous. Évidemment, on en revient toujours au développement de l'expertise. C'est fondamental pour l'Institut Quantique, mais c'est fondamental pour avoir une bonne profondeur, une bonne compréhension pour la maîtrise de l'informatique quantique dans les 5, 10, 15, 20 prochaines années à venir au sein de vos organisations. Donc, on est là pour travailler avec vous au développement de cette expertise-là et c'est le message, là, s'il y en a un à retenir encore là de ce qu'on veut faire avec l'espace IBM Quantique, c'est bien celui-là. Alors, c'était le survol de la dernière année. Maintenant, je vous le disais, on a plusieurs partenaires qui vont venir vous parler ce matin. Et écoutez, je pense qu'il y a une logique de commencer avec notre prochain partenaire, IBM, qui est évidemment l'entreprise derrière les systèmes IBM Q et entreprise qui a de très belles annonces à son actif dans les dernières semaines, vraiment des belles avancées du côté hardware, du côté software également, donc dans l'utilisation des différentes machines quantiques. Donc, pour vous en parler plus en détail, okay, je vais passer à l'anglais pour donc parler à notre prochain invité. Let me switch to English to welcome our next person that will come and talk to you, Aparna Prabhakar. She's VP Partner Ecosystem and Strategic Alliances at IBM. And Aparna, you are here this morning to talk to us about, well, partnership, I guess, and how to develop ecosystems. And so, the floor is yours.
Thank you so much. First of all, thank you for having me here. I'm really excited to speak about what we are doing at IBM and why ecosystem and partners actually matter in this. With that, let me actually share my screen. Yeah. And there you go. So just a quick introduction. I'm the vice president and I lead the worldwide partner ecosystem across for IBM Quantum. And that is the largest partnership ecosystem on quantum right now. Now, before we get started, I think first thing to understand is why is this so important? What you see here is what we believe quantum industry is going to grow by. And here are a few takeaways. On the left-hand side is our projection, which matches really well with the analyst and the managed consultants projection, is that over the next 5 years, you will see this industry grow up to 5 to 13 billion. And this is primarily driven by a few growth drivers, which you're already seeing happening. One is you're seeing a broader understanding of quantum applications. You're also seeing technical achievements in 3 areas: the quantum quality, capacity, and speed. And if you heard our quantum summit, we just made announcement of our 127 qubits with advancement in both or in all 3 areas. And then you also see a huge amount of rise of investments in quantum tech. You can see many SPACs coming up. You can see a lot of startups getting funded in the space. And fourth, which we'll talk about more in detail, is the growth of community-led quantum contributions. And that means a lot of folks are actually contributing back into the ecosystem. And it's not led by just one company, but it's really becoming a community-led effort. As I think about that, let me see. Let's talk about how we think about quantum industries. And when you go from bottom to top, we basically divide it up into 3 big areas. There's one, the quantum computer itself, there's applications, and then there's services. And you have players who are playing each of these spaces. You have end-to-end providers, you have startup who are working in software, but there are also folks who are working in applications. And as you think about IBM, we really have only one big aspect or one big goal, and that is to deliver value to our clients and partners. And we are basing it off 3 big aspects of it. We are differentiating with the computing service, which is right at the bottom. And this is where I think the next year or so is going to become extremely important, is we are bringing quantum computing workflows to data. As we think about quantum is never going to stand alone. It's always going to coexist with classical. That means that we have to work to figure out how to get quantum workflows across software, existing software tools, product, and really leverage where the data resides today. And we are really thinking about it and starting to put a lot of effort with our partners. And we see a lot of industries focused on that aspect. And last but not the least is changing the client's business with quantum computing. What does that actually mean? Depending on where you are in your quantum journey, a lot of the folks are just asking, hey, this quantum is coming up. What do we do with quantum? How do we think about it? And then there's the other end of spectrum, which we call quantum native. There are industry clients who actually have been investing in quantum. And now that the hardware is reaching the capabilities where simulators are, it's going to cross what's possible with simulators. They're sitting up and saying, okay, now let's apply it to our use cases and let's think about the quantum workflows. And that is what we mean by changing clients' businesses with quantum computing. We are really meeting clients where they are in their quantum journey. Now, this is really, now let's make this real. These are pure numbers, which are basically saying, this is really real. And there is a rapid acceleration. Today, we have 20 plus systems operating. We have 300,000 users. We have 2 billion circuits per day executions, and we are growing 170%. If you pause for a second and think, how is this even possible? I think we made it really simple in 2016 when we put our system on cloud and we really opened access to the users. And since then, the users have embraced this and have been growing tremendously, adopting and putting it back into the ecosystem. And I love this slide because it's a nice post slide. Now let's switch gears and talk about what is quantum network. We really build quantum network with threefold mission: educate and train, accelerate research, and develop applications. First and the broadest pillar of this mission is educate and train. Today, we have over 300 users who've run over 750 billion executions, quantum circuits, on 20 plus quantum computers. And they run over 2 billion circuits per day. We also have a goal, which we've crossed, is to get 1 million folks educated on quantum. And we're really putting content and tools out there, educational material, including Qiskit textbook, which enables all of that. Then comes our second pillar. This is really focused. You cannot grow in quantum as a technology if you don't accelerate research on it. And for that reason, we pull together this community of 170 plus clients and partners who are working together as a network and researching, developing things, and really pushing the boundary on quantum. With that, we've had over 700 scientific papers which have been published using IBM quantum computers. And finally, we're collaborating with some of our partners on 30 plus applications. And those are the three big pillars. Now, what does this actually mean? There's a simple message here. IBM or any one company cannot do this alone. And what that means is we really are looking to create this flywheel effect, which you're seeing here, where IBM is really going deep, advancing the platform and thinking about platform. Our partners are looking and taking those platforms and saying, hey, let me actually build applications and let me enable technology and understand how to use this. And then they guide us back, they give us feedback, which then goes into our platform, and we are building tools and capabilities. And that is the flywheel effect which we are going for. Again, as of today, we have more than 170 quantum members. This is just a list. It's not a comprehensive list, but it just shows you the variety of folks we have in our ecosystem. This is in no specific order. It's just a big list around that. Now let's talk about what does it actually mean to be a network? How does the network actually work with each other? And this is a great example of this. So going from left to right, IBM Quantum actually published an algorithm paper on amplitude estimation. Keio University looked at that and said, hey, I think I can take that and build it a little bit further, and let me advance this method. And they worked with Mizuho and MFG and really advanced that methodology and published a paper out there. JP Morgan Chase, which is in completely different aspect, said this particular work actually looks interesting and I can really play with it in options pricing. So let me go ahead and apply this methodology into a different area use case and then see how it works. And they actually advanced it in their area. And what they did was even better. They then took the results and actually contributed their entire code into open source Qiskit for everybody to use. And since then, the team has been using and pulling things together. But this talks about why being in this network is actually beneficial, because you're not working in isolation. You're actually learning from the broader network partners who are at different stages, and you are growing as a result in your quantum capabilities. let me walk you through a few examples of how this network is worked. So we just announced runtime capabilities, and Paul, who's coming after me, will talk a little bit more about that. But when we launched our beta version, we reached out to StrangeWorks, which is a startup which is creating a platform where you can access different companies' hardware together. And we said, hey, can you actually test this and put it on your platform? So they put Qiskit runtime on their platform. Deloitte, who was using them, then took that Qiskit runtime, and they had an existing algorithm they were playing with and were actually able to demonstrate 92% faster speed using this runtime while we were in beta version. And this is how the ecosystem is working, right? We gave it to a startup put it on their platform. Deloitte, which is a big GSI, used it, and now they've come back to us and said, hey, we've gotten some results, let's go that next level step, help us think through what's next. So we're working with Deloitte right now to push their boundary conditions as well. Now, that doesn't stop there. If you look at these talk about what are the different flavors of partnership. We're working with AFRL, and we are really thinking about how do we advance science and research in those areas, right? Last week, AFRL was with me in Yorktown, and we spent time talking about what does next year look like in our partnership and how do we think about that. Cleveland Clinic, we just announced that last year, and it's really focused around advancing healthcare. And Fraunhofer is our big system one. It was the first system one outside of US. And that is really to create this national ecosystem. And finally, there's University of Tokyo, which is also talking about that. Now, let me take a step further and actually talk about what does this ecosystem actually mean and national ecosystem actually mean. So we have been very strategic in placing our actual managed systems in different countries. And we've been very thoughtful about how we place and where we place. There are three things we are trying to develop. There is skills, because you cannot have an advancement in community if you don't have the skills or workforce which is being built. Second, we are trying to advance research. And third, we are trying to make sure that there are resources which are in place to do that. And if you look at all our examples, in June 2021, we inaugurated Fraunhofer. Tokyo was followed right on the heels. These are managed systems on-prem, which are in the country. And Tokyo was July 2021. Cleveland Clinic is coming shortly, and we just announced Yonsei. And there are simple reasons for all of these. One, they are actually really great research institutes in their countries. Second, they are really thinking about how they skill up their industry and their students and workforce around that. And third is a lot of them are thinking about how do we make sure that my country is really becoming the center of competence around quantum, and having a system actually helps thinking through it differently. And I would hope to see, when I think about Sherbrooke, I think about you guys in this particular area, right? I think about you as becoming one of those national centers of competence where we are creating a national ecosystem focused on quantum. And the data has actually shown us a great uptake. I cleaned this up. I didn't put numbers because I cannot technically show you the numbers. But when you look at this, this is Japan's system. And what I want you to take away is simple. We started the access, and access, once you start the access, you need a lot of skilling up. So it's not surprising that you have these dips and curves on it. But since the system has actually been deployed, there is a 5x increment in system deployment. This has resulted in amazing number of industries. There's been huge amount of research papers, and there have been a lot of engagement on skill building as well. Those are the three primary things they've been focused on. And you can see a huge adoption curve change, and it's shifted how Japan is growing in that area on quantum as well. Now, this is my last slide. And what do you want to take away from here? It's simple. There are four big things. When you think about IBM, and I will say this, I believe this is 100% true. We are leading in terms of access to quantum technology. And what we are really, as you partner with us, you're getting access to real quantum hardware. You're getting a good technical collaboration with some of the research. You're getting one of the most powerful SDK tools and hardware. And last, but probably the most important initially, is you are getting educational resources for quantum, which help you skill up and then get quality output there. And that's IBM Quantum. I'll stop the share and open up for any questions.
Thanks for that, Aparna. So if there's any question, you can put them in the chat, and we have a few minutes for Aparna to answer them. So we'll leave you a few seconds here. Anyway, if questions don't come, what we could do, well, right away, what we could do is you put them in the chat, and well, since our next person that's going to talk to you is also from IBM, I guess that we could have the Q&A section for both of them afterwards. So let me introduce you next to Paul Nation. He's a Director Technical Enablement Program at IBM, and he's going to talk to you about the roadmap in quantum I referred to a little earlier. So Paul, the mic is yours.
Thank you very much. Good morning, everyone. So yes, this is Paul Nation, research staff member at IBM. And I'd like to talk to you about our roadmap. We recently updated it within the last week, and in particular with a focus on reaching quantum advantage. Now, to begin, we have to, of course, make sure everyone is on the same page and define what we mean by quantum advantage. And loosely put, this is the point in time at which a quantum computer can outperform classical computing resources of any kind in one or more limited real-world use cases. Okay, so it's not going to solve everything right away, but maybe in one or two key areas you can show advantage. And so advantage comes in a couple of flavors. There is, of course, the wall clock time is faster. It just executes things faster. It could be a cheaper solution, or it could be more accurate, or any combination of the three. And that's kind of the loose definition of what we mean by quantum advantage. So the next question is, how do you know that you've reached quantum advantage? And again, it depends on who you talk to. In an ideal world, there would be a very rigorous mathematical proof that given this quantum algorithm or application, I can rigorously prove that there is no classical method that one could devise that does it in a faster runtime, cheaper, etc. Okay, and there's a star next to that I'll get to in just a second. The other hand is a more applied approach. And one could say quantum advantage is the point in time that someone will pay me money to run a commercial, industrial, or heavy duty research application on my quantum machine. And so it surprises a lot of people to learn, and this is why the star is here, that the first rigorous proof of any quantum algorithm being provably faster or scalable than a quantum algorithm was actually only in 2018 by Sergey Bravy and others at IBM Quantum. Okay, so these kind of proofs are very rare. And so the ideal rigorous mathematical proof may not be there for algorithms and applications where They're run on noisy machines, and there's lots of hybrid activity between quantum and classical. But this is our notion of quantum advantage. So what are the use cases that might be first on the roadmap to quantum advantage? There's a couple that look like they're within range. The first in the upper left here is quantum machine learning. There's a lot of activity in quantum machine learning, to say the least. That is a very fruitful avenue that's being explored now. Chemistry, applications, materials. I have a picture of airplanes here. Airplane wings have actually been looked at in terms of their composite structure on a quantum computer. Also logistics of routing, which of course also happens for commercial airline travel, is also there, and medicine, healthcare, et cetera. Okay, and so these are the applications, and we try to, of course, reach this milestone of quantum advantage. And then usually people think of this in the context of, oh, we need more qubits, we need lower error rates, et cetera. But it turns out it's not that simple. Okay, if you want to actually try to achieve quantum advantage in one or more of these areas, you really need to proceed in multiple directions simultaneously. And so the IBM roadmap is really designed with this notion in mind that progress cannot be made in a singular direction. And we have to take a multi-pronged approach. And so there are a few key metrics that help guide you down this road to quantum advantage. And I have three of the primary ones listed here. The first is what we like to call quality, which is basically a measure of how well does my quantum hardware implement the circuits that I give it to execute. At IBM, we like to write this as a notion of quantum volume. And you can see some of the quantum volume numbers there. Back in 2019, we started with a quantum volume of 32, which is an algorithm over 5 qubits. And then we've moved on to 7 and 8 qubit quantum volumes today. And we aim at doubling this value every year. The next is scalability. And of course, this means the number of qubits that you can have in your system. It actually means a bit more than that, we'll get into later. But the number of qubits is kind of the thing to keep an eye on there. And then lastly, speed. All right, if my machine is very good and it has 1,000,000 qubits, but it takes an hour to run a gate, it's not a very effective thing to try to reach quantum advantage on. Okay, and we'll talk about speed as well. It's a multi-pronged approach there as well. All right, so to dive in, let's just talk about quality. So here I have a very busy slide, so let's break it down. So on quantum computers, one of the best metrics to gauge quality, okay, outside of something like quantum volume, is the error rate of their 2-qubit entanglement gates. On IBM machines, this is the C0 error rate of our machines. And so what I've done here is I went back and I looked at all of the historical data we have for all the machines that are 20 qubits and higher that we've released in the last 3 or 4 years or so. And I plotted them here on a log scale plot, okay? And so what you can see is that back in 2017, our first 20 qubit device was called Austin. The topology of this device, which tells you which qubits are connected by these C0s, is in the lower left-hand corner here. And this little hexagonal cross-shaped topology. And as a function of time, you move to the right, of course, and you can see that the error rates represented by these dots, each color coded with respect to the processor revision, go down. And early on, they go down at a fairly linear rate, which on a log scale means we're doing exponentially better every year, but only weakly so. And then you can see somewhere around January to July of 2020, you see that the slope has gotten greater. You see this inflection point, and it's more or less represented by the collection of white dots. That is when we introduce what we call the heavy hex architecture. This is an architecture designed to minimize errors in our machines and also be compatible with error correcting codes. And since that time, we've been able to greatly increase the rate at which we reduce the errors in our systems. And so you can see that further revisions, for example, the next revision is the green dots, which we call Falcon R5. And then later on, the test devices, which are the yellow dots, you can see that the error rates are extremely low, ending with the Falcon R10 at the bottom there, which has an error rate for a 2-qubit gate of less than 10 to the minus 3. Okay, and so these are all very stepwise introductions of various things, such as interference couplers, tunable buses, and finally coherence updates that allow us to make these advancements. Okay, and you can see the trend is a very strong exponential decrease in these error rates going forward. Okay, and this is very much what we'd like to see, because already here with the Falcon R10, we've reached the error rates where one can start contemplating things like demonstrations of basic error correction codes. Okay. Now, if you have quality, that means you can actually do stuff with it. Okay, and so over time, we've been able to do more and more things. I've just put a list of papers here on the right that demonstrate some of the things that are possible on our 27-qubit machines. An example is given there on the left. And so beginning some time ago, this is more technical things, demonstrating buried gates and things like that. But as you get closer to now, the last paper there is dated May of this year. You see that we've been able to now switch over things like basic applications and algorithms. For example, quantum machine learning and demonstrations of things like quantum kernel alignment methods. Okay, so we have exponential improvements in our quality metrics, and then this is demonstrated in more and more advanced research that we're able to do on the systems as a function of time. Okay, so with that, I want to leave quality alone for a minute, because quality is something that I think most people have a grasp on, and now I want to get to the scaling aspect. Okay, so here's the latest picture of our roadmap in terms of scaling. This is, of course, concentrating on the number of qubits. So back in 2019 is when we introduced this heavy hex topology. And then later on in 2020, this is where we started seeing this inflection point, and when we started introducing another architecture that's also based on heavy hex called Hummingbird. And then, of course, as you go on, you can see the roadmap out into the future. But here in 2021, just a week or so ago, we introduced to the world the 127-qubit Eagle processor. And each of these things is a revision on top of the last one with a particular goal in mind. So the 27 qubits was the introduction of a new topology. Our Hummingbird processor is actually introducing scalable readout in terms of multiplexed readout, fewer lines going in and out of the refrigerator, for example. And of course, the 127 qubits is all about packaging for large scale. And of course, beyond, there's other stuff. But what I don't like about this slide is it only goes back to 2019. It doesn't really show the advances that we made. So on the next slide, I actually want to look back a decade, okay? And so on the left here is a 3-qubit system that IBM made back in 2011. Okay, and you can see it looks very much like a device made in a laboratory. Okay, and now on the right here, this is it's not a real image, of course. This is a computer mock-up of how our 127-qubit Eagle processor is made. Okay, and you can see within this decade that there is a huge advancement in how we make and design our quantum processors. Okay, and so what we have now is a 3D architecture. If you look below the cap here that says IBM Quantum, you see the plane that our transmon qubits are on. They're each connected to each other by a bus. On the layer below, we have our readout resonators. Okay, they're on a completely separate plane to minimize noise and to save area. And then finally, down at the bottom there, we have what we call the wiring plane. And it is a bit hard to see, but there's fingers in this wiring plane that are called through substrate vias that actually poke into the upper layers to make the electrical connections. Okay, so this is very much a 3D design chip that leverages a myriad of CMOS packaging techniques. Okay, so this is how we design our processors. this is how we envision doing the scaling of these processors, but it turns out that this is not enough for scalability, okay? Because we are not in the fault-tolerant regime, as well as we can make our processors, they still have noise, and if we want to reach quantum advantage, we have to learn how to mitigate that noise, okay? And as the processors become bigger and bigger, this mitigation strategy has to also be scalable, okay? So it's not just the processor itself, but it's also the techniques that need to scale. And again, this last year, we've made a couple advances in this. One of the ways to mitigate errors is to try to reduce the effect of errors in your gates on the final outcome of your computation. And we do this via something called zero noise extrapolation, where you stretch the amount of time your gates take, you collect a couple data points and extrapolate back to effectively a stretch factor of 0, which equals zero noise. And so we demonstrated this out to 26 qubits on over 1,000 C0 gates. And we had to do a bunch of other tricks just to get zero noise extrapolation to work. But what we demonstrated was in that doing all of this, you can achieve an accuracy on a real device that's beyond what is possible using tensor network simulation methods, okay? And so what this allows one to do now is begin to think about mitigating those errors that you do have out to numbers of qubits where quantum advantage might lie. Now, it's not at 26 qubits, it's beyond that, but this is the first step down that road. Next is measurement mitigation, because of course we have gates and your circuit goes through the machine, but if you want to get your hands on the answer, you got to take the quantum information and bring it out to the classical world, and that's done via measurements. It turns out that measurements have roughly the same noise as a C0 gate on our machines. And since you always have to make measurements, it'd be nice to get rid of that error too. Measurement noise is a bit easier to deal with because it looks just like a linear system. And so it's kind of a classical correction scheme at the end of the day. Nominally, it scales exponentially with the number of qubits, so with the Hilbert space dimension. Recently, we were able to find a trick that reduces this, so it's no longer exponential in the number of qubits, but rather linear. And so what we were able to show is that using a simple laptop in about a second and a megabyte of memory, you're able to correct errors that would be impossible on even the largest of our current supercomputers in the world, okay, by a factor of about 100x. And so this is nice because this shows we can also scale our measurement mitigation very nicely. And this is also compatible with the gate mitigation stuff I just showed you. So you can combine measurement error with gate level mitigation into something that will mitigate errors out to, again, where you would expect quantum advantage to lie. Okay. So the final of the trio is speed, okay? And speed is a very simple thing to ask about it. You know, how fast can a quantum computer execute my circuits in a faithful manner? But it turns out one has to get into the weeds a bit about what this actually means. If you're running an algorithm or application today, what happens is you usually have a circuit that's parameterized that you would like to update your parameters for. I take my circuit, I update its parameters, I have to send that circuit now to be converted into waveforms, loaded onto my pulse generators, and then executed on my quantum processor. And this whole process takes some time. And so the natural thing is, how long does it take me to run cycles of this over and over and over again? We recently have introduced a metric to compute this, which we call circuit layer operations per second. It's called CLOPS, which, if you know floating point operations per second or FLOPS, it's obviously meant to remind you of that. It's done in a particular way that we don't necessarily have to get into, but it's related to quantum volume, where you measure how many layers of a quantum circuit, quantum volume circuit you can execute per second. And so this is a hardware agnostic thing. So anyone can go and measure this on any piece of hardware. For our IBM systems, we have measured this on all the machines. And if you go online to the IBM website, you can see these values posted for you. Here I've highlighted two for our Hanoi machine and Toronto machine. And so you can see how many of these circuit layer operations per second that these machines can run. Okay, and you see that they're in the thousands range, 2,000 or so. But there's no limit to this, to be in this 1,000 range. It's easily increasable by orders of magnitude. And these are the other things we have to consider when trying to get to quantum advantage. So how do I know I can increase those by orders of magnitude? Well, it turns out if you go and you run a job on one of our machines and you go and you break down how long it takes to run a job, it turns out that when I submit a job, only 5% of that time, roughly, is actually spent running on the quantum processor. The rest is, this pulse generation, storing to cloud databases, et cetera. And so no one would be expected to reach quantum advantage if 95% of your time is wasted doing stuff it doesn't have to do. And so one solution to some of this, not all of this, is to not do what we currently do today, which is a user takes a circuit on their laptop, they send it to IBM Quantum, we do some stuff and we send it back. That is a very expensive thing to do, especially if you're doing something like an iterative algorithm where one has to loop, up to several thousand times, let's say, and you're bound by IO overhead. So the logical conclusion is, well, let's not send a circuit, let's send an entire program of classical plus quantum computing instructions. And then you upload that into the cloud in a Dockerized OpenShift type infrastructure. And that's kind of what I've drawn here. We have the user here on the left. They send a program, not circuits, but an actual program. Think of it as a Python script, if you will, into the cloud. And then instead of saying, here's a circuit, say, run this program for me. That program goes into a queuing system, it waits its turn, and then it goes into this execution layer that does usually iterative loops in a very, very low latency connection to our hardware, okay? And it turns out that if you do this, you can get dramatic improvements over the naive way we've been doing things for several years. We ourselves have shown over 100x improvement on variational chemistry problems, just using this technique to reduce the IO overhead pipelines and additional enhancements that this brings. And so this notion of running entire programs in the cloud is definitely where we see the future of quantum going. Okay. So what does this mean to a person in the real world? That is, of course, important. And so we've actually looked at this. So here I have a plot of an execution time of an experiment that we did in 2019, again, quantum chemistry. At the time, that particular experiment took 3.1 billion circuits of data to generate the plots and stuff for that paper. If you ran that today on various hardware, this is the kind of numbers you would see. So on IBM machines, these 3.1 billion circuits would take you about 172 hours in a runtime. Rigetti, we have to, of course, estimate it's about close to 500 hours. And then for trapped ions, because their gate times and cooling require a bit longer, the same calculation estimated from the paper I've shown you below would take about 3.5 years to run the same calculation. Okay, so this is why things like runtimes, things like circuit layer operations per second actually make a big difference when you're thinking about quantum advantage. Even if you're working on trapped ions that to date have better error rates than superconducting circuits, if your algorithm takes 3.5 years, that may not be a good enough justification for using that platform. Okay, so there's a lot of things to consider when thinking about quantum advantage and how to get there. Now, right now we're working on runtime, and that is definitely where we see the future, but the runtime itself is probably not the end story. And it's not because, as I mentioned, it works in a Dockerized environment. And this requires the end user to know what kind of resources your program needs, how much memory, does it need a GPU, does it need a QPU, etc. And so the runtime will naturally evolve into something else that we like to call serverless computing. And in serverless computing, you have the same kind of thing as a runtime. So you have something that typically loops over classical and quantum resources, but then it's all orchestrated by the cloud itself, where the cloud decides how much classical and quantum resource you need, and it will scale it automatically. So there's no infrastructure management that you need to do. It will scale automatically, and you don't have to worry about things like, how much memory did I allocate, how much disk space do I need to save the result, etc. And so this is kind of the future that we've announced again last week, where we really see things going. Because if you look at algorithms at industrial scales, it really requires not just a quantum processor that goes fast, as we've talked about, but it also requires really HPC resources. If you're doing chemistry, computing integrals and things like this needed just to map the chemistry problem into something the quantum computer understands, requires very, very high degree polynomial overhead computations. And so at some point, you really need to glue all these things together in a seamless fashion. And runtimes plus this serverless orchestration is really the future of where quantum computing has to go to be industrial strength. All right. So I've went through everything in terms of our three metrics, and I was asked to talk about the roadmap, and here towards the end, I finally give you the roadmap slide. And the reason we went through everything ahead of time is because this slide has a lot of information on it, but we've covered most of the stuff here in a more practical fashion. So everything we talk about basically covers these areas of the IBM roadmap. We talked about our systems, we talked about scaling and quality. We've also talked about scaling in terms of error mitigation techniques and speed, Qiskit runtime, and IBM Cloud plays a role in not only the runtime, but also in this notion of serverless execution and seamless scalability. Okay. So the last thing I want to end on here is this slide. So one can actually ask yourself, is our roadmap good? Does it lead anywhere of interest? And so we asked our friends at the Boston Consulting Group, pick apart our roadmap and see where it takes you. And so what we see here is their predictions on value based on the IBM roadmap going forward, in particular in different areas of applications, materials, drugs, services, and stuff yet to be defined. And the numbers here go out to 3 billion plus, starting, for example, with an inflection point at 2022. I'm not a business person, so the numbers don't excite me so much, but rather I like to use this as kind of a map of where we are, right? So if you said, where am I today? This is this red arrow here. And what's nice as a scientist about this is you can see that we're 1-2 years out from this inflection point, which means that if I am working on algorithms applications today, by the time I've worked all these things out, they will be ready in time with this inflection point hits, right? So kind of right now is prime time for working in this field, because if you start now or you continue on this path, we're very close to this point where everything comes to fruition, and then the field really begins to take off. So now is a very good time to explore things. And so with that, I thank you.
Well, thanks a lot, Paul. That was fantastic. And it's incredible how each time I hear you folks at IBM talk about your systems, I always learn more and more. And you always have new things to tell about the systems. It's very interesting to follow what's going on. We have a question in the chat. I guess this one's for you, Paul, asking about the systems that you have, the quantum systems, of course. And the person wants to know if they work as standalone units or if they are closely connected. You talked about how classical computers are connected to the quantum computers, but what about quantum computers between themselves?
Well, so that is, so today the computers do not talk to each other in a quantum way, right? They are physically located. I don't have my slides. The first slide, you actually saw a row of these guys. So they're close in physical space, but they do not talk to each other. So For a long time, people have thought about how do I connect one computer in a refrigerated canister to another one in a quantum coherent fashion. This is still work that's ongoing. A lot of people look at this, including ourselves. And so right now, they do not talk in a quantum coherent way, but in the future, they necessarily will have to. And so that's an open area of research.
Oh, great, thanks. Well, it was the only question in the chat, but at the same time, we're right on the 10 mark. So I guess that we are going to end this first session with you two here. Thanks a lot, Aparna. Thanks, Paul. It was great having you this morning. It's great working with you on a daily basis and having all these resources at IBM that you have that we can rely to when we need. So I guess that with this, we'll move to our next speaker. We are going to move on, the partners that we work with within the hub now. She is from Lockheed Martin. Danny Cougar is research engineer manager for Lockheed Martin Quantum programs. And Danny, you were going to talk to us about, I guess it's going to be twofold. Of course, you are a new hub member here at Sherbrooke, and we also have a research project that we are going to conduct together. So Danny, if you will.
Great, thank you so much, Jason, and thank you so much to Sherbrooke for having us here today. Let me just go ahead and share out my screen. All right. So yes, first I'd just like to thank everyone for this opportunity today to speak. We're very excited for this program and very excited to move forward, really to address multiple intractable applications core to our business through our membership here with IBM Q Hub at IQ. As a global R&D company, Lockheed Martin operates across 4 business areas: aeronautics, missiles and fire control, rotary mission systems, and space. Our quantum engineering, science, and technology team is organized in the same fashion across those groups with focuses on applications core to each one of those lines of business. Now, I myself am the quantum technologies lead for our missiles and fire control business, and my team collaborates with my partners from those other business areas, coordinating really across our functions as a corporate-wide team under our lead for all of quantum at Lockheed Martin, Dr. Kristen Pudens. Now, as you see here on my main and only chart, Lockheed Martin's quantum programs encompass quantum computing, sensing, and communications. But for the purposes of today, we will focus on LM's research and development in quantum computing found in this top box here. Now, Lockheed Martin has been actively working in quantum computing applications for more than a decade, internally through our core quantum team, but also externally with our partners across the globe. And as a result of these internal programs, we continue to evaluate emerging quantum providers. And Lockheed Martin seeks quantum computing access that enables our industrial applications development during this noisy intermediate scale quantum hardware phase of computing. Now, Lockheed Martin has been evaluating the IBM quantum hardware for years, but with recent hardware and software advances, we really wanted to target a more formal access program for our cross-company quantum teams. And at this stage of research, it's imperative that we find the right partners to collaborate with outside of Lockheed Martin that support both our research and our workforce goals. And that is where the IBM Q Hub model really comes into play. We've been able to see success in the past pairing access to quantum hardware with a university collaboration, really to deliver better results and create a greater impact to the quantum ecosystem. So for us, access to IBM quantum tools as a member of an IBM Q Hub is by far the best framework for Lockheed Martin to drive results for our customers. And while the IBM Q network is global, and so is Lockheed Martin, we were really drawn to IQ Sherbrooke. We've collaborated in country quite a bit and had formal research collaborations in quantum technologies in the past. And so we really think the research capabilities at IQ are a great fit to build on this type of collaboration. So let's get into it a little bit. So there are a number of realities when working on the bleeding edge of technology development, and quantum computing research is definitely not immune to those factors. Today, I'll focus on two of those realities and how Lockheed Martin's membership in the IBM Q Hub at IQ and the collaboration with Sherbrooke and the research quantum teams are set to address each one of these realities. So first and foremost, I think to no one's surprise, Lockheed Martin is currently in a very challenging reality of increasing complex environments and different challenges. As a result, we are pursuing quantum computing development programs that seek to address multiple behind-the-scenes applications as well as real-time tactical scenarios that are core to each one of those businesses I described earlier. So like much of the quantum community, our research is organized in three main development areas. That's machine learning, optimization, and chemistry or material simulation. So for machine learning, we're focusing on hybrid classical quantum algorithms that can enable things like target detection, autonomy, and controls. For optimization algorithms that really abound throughout Lockheed Martin's business, we're developing quantum algorithms that impact things like logistics, resource allocation, and different manufacturing efficiencies. And lastly, the simulation of materials and chemistry really map natively to quantum computers, where classical memory resources and computation times really grow exponentially for a breadth of Lockheed Martin applications. So we do have a path to seeking different advantages in that space. So with that being said, of those sort of our three areas, our membership here will drive our development by accessing the latest and greatest hardware from IBM and seeking quantum advantage together with Sherbrooke. While we look forward to finding areas of common interest and collaborating really across all those different areas with IQ Sherbrooke, there, like Jason mentioned, we do now have a formal research engagement that we're pursuing as a partnership that entails development specifically on quantum optimization algorithms. So the second reality I'd like to address today is workforce. During over our decade of experience in quantum computing, it didn't take long for our internal team to realize that aligning the right talent to our quantum research goals would be as important and perhaps as difficult as the research itself. It's become clear to us that there are not enough PhDs graduating in quantum technologies to staff our needs and staff the needs of the greater quantum computing ecosystem. So as a result, we must make a focused effort to address quantum education and workforce needs for not just Lockheed Martin, but for the greater community. Now, I am not saying that we don't hire quantum PhDs, because we do, but we also have over 60,000 engineers here at Lockheed Martin. We need to look at that talent pool to be trained to become what now we call quantum engineers. And actually, that's how I find myself here. I don't have a formal background or education in physics or quantum technologies. My background is in computer science, mathematics, and system engineering. And for the early part of my career, I supported Lockheed Martin programs as an engineer. And upon being introduced to quantum and the projects here at Lockheed Martin, I was mentored by our quantum experts and sought out opportunities to bring together engineering and quantum for our different lines of business. And the reality is, mine's not a unique story, and Lockheed Martin continues to learn from these experiences to set up quantum education opportunities to train our workforce. Whether that's a quantum computing 101 courses that we record and make available across our company, or setting up development environments that now are a sandbox for all engineers to learn quantum computing firsthand. So where does the IBM Q Hub at IQ come in? Well, IBM has created an infrastructure that brings quantum tools to the hands of what we call quantum curious engineering teams. Again, people that may not have a formal background in physics or quantum. And the access and partnership with IQ allows us to integrate those tools into our internal development environment. In addition, having a team on the IQ side that we can meet and discuss lessons learned, different situations, or deployments that we're doing as we all ramp up using these different tools as they're made available to us. And even in the short time we've been a member of the IBM Q Hub at IQ, this access has enabled us to launch an internal quantum computing innovation contest, or hackathon, if you will, focused on putting IBM quantum tools in the hands of our LM engineers seeking to address real R&D challenges across our business areas. So these engineers have 8 weeks to learn, develop, and deliver results using quantum computing tools. And the Lockheed Martin quantum team gets several benefits here. One, we are educating new quantum engineers and learning, honestly, a lot about how to educate engineers around quantum technologies. And two, we're identifying additional areas where machine learning, optimization, and material simulation can inform our path to finding quantum advantage. And finally, we are demonstrating how access to quantum computing tools through the IBM Q Hub at IQ, for example, can drive quantum education and workforce opportunities internal to Lockheed, but also hopefully inform outreach going forward. So we know that IQ also has a focus on quantum education, and we look forward to sharing our lessons learned, participating in partnerships and outreach, and really moving forward to grow the talent in country as well as in our teams. So this is really where we find ourselves today at the beginning of our IBM Q membership and collaboration with IQ. We're focusing on, quantum research and workforce, but I'm confident that this is really just scratching the surface of what this new partnership will offer Lockheed Martin. So with that, I would like to thank everyone for your time today. And again, thanks to Sherbrooke for bringing this open house together. And we really look forward to all that is to come.
Well, great. Thank you very much, Danny. It is great having you on board now. And yeah, well, it's just starting. As you said, it's just a new partnership that we are working on. And yeah, well, a lot of things are ahead of us, and well, probably exciting science here to well, in the first place. So if there is no other question, I guess that we will go on. And well, thanks a lot, Danny. Our next speaker from CMC Microsystems, also a hub member here at Sherbrooke, Hudson Mendes. You are team leader quantum computing at CMC, and well, you're here to talk about, well, your activities in the hub. Hudson?
Hi, Gisela. Thank you very much for the very nice introduction. Bonjour tout le monde. That's my extent of French that I can say at this moment. So I will start by introducing CMC. Can you see the slides now and the sharing full screen?
Yeah. Yeah.
Okay, thank you very much. So I will start introducing CMC Microsystems and move down to what we do with quantum computing. So CMC is really an enable entity. So we do activities such that to lower barriers to do technology adoption in Canada. So this means that we provide tools, service for research and companies to adopt new technologies such as quantum computing. So CMC started back in 1984, and we do manage what is called Canada's National Design Network. And what we do is to provide infrastructure for innovation. And this basically means that CMC has a few services on different technologies, such as artificial intelligence and machine learning, MEMS, microelectronics, photonics, and since September last year, a little bit before, sorry, July last year, we are started quantum computing service by becoming the first member of the IBM Q Hub at Statistique Quantique. If you want to learn a little bit more about the technologies that SMC has, please go to this website to learn more about all those technologies. So what you do is do advanced technologies, and we enable research in Canada by providing tools and service, and those researchers in Canada, they work in a wide range of areas and different fields of research, such as clean technology, advanced manufacture and digital industries, health and bioscience, and agri-food, and many others. This is just a small example of the activities and research that SMC enables by providing infrastructure for research in Canada. So we manage the Canada's National Design Network. It's basically a Canadian-wide collaboration between 65 universities and colleges to connect 10,000 academics with 1,000 companies to design, fabricate, and test micro and nanosystem prototypes. In the last year, basically 2020-2021, the research members of the network, they published more than 4,000 articles. They were awarded 150 awards. They awarded 80 patents, 430 collaborations with industry. We enabled 14 new startups, and with the training that we provided at SMC, more than 700 students moved from academia to industry. So we are across Canada. So in basically all provinces and territories in Canada, we have collaborations with research in all of them. We have a lot of collaborations with post-secondary institutions, companies, and many of them are companies that do manufacturing micro and nanosystems in Canada. So annually, we basically have more than 1,000 professors connected, almost 7,000 researchers. That includes professors at academic institutions, in companies, and of course, PhDs in at the universities and masters as well. So we provide computer-aided tools, and we have more than 7,000 users for those tools. Last year we had more than 270 prototypes in photonics, microelectronics, and MEMS device, and now we're starting a new service for fabrication of quantum device, and we also rent equipments for research across Canada. So to enable all those research in Canada, we need a global a worldwide industrial supply chain, both in fabrication and providers of CAD tools, and of course equipments for research. So we collaborate with many countries to enable all this research in Canada throughout the FAB and CAD partnerships. For example, we have partnerships with global foundries for microelectronics and photonics device, and soon we're going to announce also some foundries for superconducting for the fabrication of superconducting quantum device. We enable research by also connecting with many organizations throughout Canada and throughout the globe. So here, for example, Chiang it's a fabrication microelectronics fabrication facility in Bromont, near Sherbrooke, and Isaac in Quebec as well, Optonic in Quebec City, and many others I can mention here at this time. So Quantum started last year, last July, when we became a member of the IBM Q Hub at Statistique Quantique in Sherbrooke. And basically, we start first with software, and now we're starting to add hardware service as well. So what we do is to enable research in Canada. So this means that we work in very close collaboration with academics and industrial partners to create novel quantum algorithm solutions and quantum hardware. As I mentioned, we started with IBM Q Hub at Statistique Quantique, and in January 2021, we also started a collaboration with Xanadu, a Canadian a startup, or not a startup anymore, but a Canadian full stack company, quantum computing full stack company. And the software part, we develop quantum algorithm solutions for a wide range of projects in research fields such as biology, chemistry, physics, and quantum machine learning. More on the fabrication side, we provide access to computer-aided design tools to facilitate the design, simulation, and validation of quantum hardware. And a new service is coming soon, is what's called multi-project wafer fabrication service, which includes process design kits, development for superconducting device. I will explain a little bit more in details all those topics in the next slides. So as I mentioned, we started back in July last year. We already have 10 projects with using the resource at IBM Quantum Hub with 6 different universities and 2 startups. Those universities are listed here. So University of Ottawa, Toronto, UBC, Calgary, Rice University, and Lakehead. And the startups are Laplace Insights and Novembre, and the Xanadu. And with the Xanadu quantum computer, I have 3 projects with 3 universities and 1 startup. And for the Xanadu projects, we have a project at the University of Toronto, Queen's University, and University of Sherbrooke, and also a project with Laplace Insights. So we are enable research in all those locations, professors in chemistry, biology, computer science, and physics, as well, and mechanical engineer at Calgary University, for example, where he studies reservoir simulation using quantum computing right now. So just to give a more broad view of the projects that we do, for example, with the startup Novembre in Ottawa, and we utilize IBM Quantum Hub resources. The goal is to develop a user-friendly graphical interface for quantum binary classification. And SIMC, in this case, SIMC, we developed a quantum solution, and Novembre integrated the solutions on the cloud-based interface. Here's just some data that we do use this binary classification, not going into details here. But the goal of this project is really to democratize the use of quantum computing solutions. So since this is going to be a graphical interface, you don't need to know exactly what is running in the back end, what's the quantum algorithm. What you need to know is to input your data on this graphical interface and choose how you're going to do your quantum machine learning solution for it. In this case, right now, we just have this binary classification here using a single qubit just for demonstration. But in the future, Novembre plans to expand this concept to different applications, such as quantum chemistry, simulations of molecules, and many others that can benefit of this kind of graphical interface. So the people that will use this graphical interface, they don't need to know quantum computing. They don't need to know to program a quantum computer. So they just need to understand the data and to use the tool or the program behind it, such as, for example, quantum machine learning classifier, or in the case of quantum chemistry, some VQE algorithm that you want to choose to train your data to get the energy spectrum of your molecule, for example. With Xanadu and Laplace Insight, we look at trajectories of the financial market. So one of the main challenges that we have is to identify and predict financial markets regime changes. So a market regime is defined as a set of features describing a process that drives the financial market returns. So to understand the drivers of the market returns is the foundation to investment portfolio management. So the goals of the project is to develop a quantum computing solution to detect these regime changes, as is shown here. Not going into details of how we obtain these results here, but this is just basically the time as years and months pass and how the market is behaving, and with the change that we can observe throughout some, for example, COVID or the financial crash in 2008, what drove those market changes. So CMC is very active in the training of the quantum workforce. We collaborate with Quantum BC and QSciTech that are great programs at UBC and University of Sherbrooke, respectively, and of course the Institut Quantique at the University of Sherbrooke. So we have this yearly gate-based quantum computing using IBM Quantum. Last year, or this year, sorry, in January this year, we organized a quantum chemistry workshop, and next year, next January, we're going to have a quantum machine learning workshop. And while you have a very advanced topic here, we teach the students how to program IBM quantum computers using Qiskit. The students also have the opportunity to learn some project management and communication skills during the workshop. And we gave an award for the best poster for this workshop. And in the summer, July this year, we organized again with those institutions here, the Superconducting Quantum Device Fabrication Workshop. This was the world's first to teach students how to design, simulate, fabricate, and test quantum device, in this case, superconducting device. We had 23 students, 19 Canadians, 4 international attendees, with 2 students and 2 companies. Again, we also teach, the students also learned project management and communication skills during the workshop. And we at CMC, we provide support to the students with access to CAD tools and fabrication of quantum device. And if the students is at the university that doesn't have access to a cryogenic lab, CMC is working with the Quantum Hub lab at Institut Quantique to provide a way for those students to access and test the device that they're going to receive in March next year. So those workshops, we have a plan to run them every year. So it's a very good opportunity for students that are start to learn and get started with in this new field. I just want to see the time here, sorry. So again, for the quantum device fabrication, CMC provide the CAD tools for design, simulation, quantum device, and we're creating the first multi-project wafer fabrication service. What that means, so we have a wafer here, and the wafer have like many designs here, and this multi-project, so each one of the designs here is a different design from a different professor, a different research group, or different student. So what's the advantage here is that the professor, instead of buying the full wafer with the designs, just buy a small area here, and this really reduces the costs for the professor to get access to state-of-the-art technologies. We do this in all this, in many areas, as I show here. We do this in MEMS, microelectronics, and photonics, and we're having now for superconducting on device. In addition to this fabrication service here, we do what's called process design kit, which is just a set of files used in within Foundry to model the fabrication process. For example, we're gonna next year we are working with IT at University of Sherbrooke to offer fabrication superconducting device, and we can create a set of files to model the fabrication process for the superconducting device. Those kits are used by researchers in Canada to design their device, and those kits are used for us to do some design rule checking. So in this case, we just verify if a specific design meets the constraints imposed by Foundry. So all this CMC can do, and you are working with foundries across the globe to provide access to quantum device. And next year, together with IT, you're going to be able to offer this to Canadian ecosystem. So just as my last slide, as a final remarks, so our mission is really to democratize access to state-of-the-art quantum hardware software technologies to different sectors of the Canadian ecosystems. If you want to learn more about CMC, please visit the www.cmc.ca. Please feel free to contact me at any time at this email. And we do have an open position here that if you're interested, please please visit. And if you have any question regarding the position, anything, just contact me. Thank you very much.
Well, thank you very much, Hudson. We have a question for you from the discussion panel. Is the Novacine cloud-based solution free for use for students, free to use for students?
Yeah, so it's still in the development phase, so it's not even available. We're just working the development, but we hope with this very simple model it will be made available to everyone as a demonstrator.
And do you think that the future of quantum computing will go toward these user-friendly interfaces in which you don't have to, I'd say, understand quantum computing to be used? Or do you think that, well, in the near future, you'll have to understand quantum at least a little bit in order to be able to use quantum computing?
Yeah, that's a great question, Gisela. I do think people, users, they still need to understand quantum computing to be able to choose the right tools to use for their application. But I also see in the future moving to more these user-friendly graphical interfaces as well. But you still need to know how the tools work in the back end, so you can exploit the maximum, and be sure that you're using the correct tools for your problem.
Okay, and there is another question in the Q&A which says, we have developed models using traditional computing. How do we transition these to quantum? Do you have a take on this one?
Yeah, so quantum computing is a different model of computing. We take some examples that exist already for classical computers, such as Hierarchical method that was created to simulate molecules, in classical computing, and you try to do something similar for quantum using quantum device methods, but it's not a one-to-one translation, and it's going to be in a new. What is exciting is a new field. There is a lot of open questions, and new algorithms is going to come as we evolve in time.
Okay, thanks. Well, I guess this is about it for the questions. Well, thanks a lot, Hudson, again. And well, it's great working with you in the hub. I know that your developers do have like regular meetings with our developers in the team here, and it's always something that they look forward to exchange with you and see how things can go further. Thanks a lot.
Thank you very much.
Great. Our next speaker, Zachary Zanussi, is from Statistics Canada. We said earlier that, well, of course, in the hub, there's hub members, and there's also projects that we work with partners, like we work directly, and Statistics Canada is a great example of that. And well, we're just about to finish a project with you, Zachary, and I'll let you talk to us about how this project came to life and what the results are. Well, Zachary, it's all yours.
Thank you, Ghislaine. Hopefully everyone can see my screen. Thank you for, awesome. Thank you for inviting me here. I'm really excited to talk about our work. As Ghislaine mentioned, this is a project that StatsCan has completed in collaboration with Institut Quantique, as well as another partner in the Bank of Canada. So this is actual work that we are just about to complete. A little bit about me, I guess. I'm a data scientist here at StatsCan. Consider myself very lucky to have worked on a quantum machine learning project in this organization. My background is in quantum machine learning, quantum information theory. So it's lucky that we got to work on such an interesting project here at StatsCan. So just a brief outline. I'll start with why, why we're all here, right? Why anyone would be interested in quantum. And then I'll talk about why StatsCan is interested in quantum. And then we can go over the problem that we set out to solve and some of our results, and then maybe give some advice for organizations interested in quantum on how to proceed to build your quantum capacity. So first of all, I'm probably preaching to the choir here, but why would we be interested in quantum? Well, it's this novel computing paradigm. It's posed to revolutionize high-performance computing. We've seen a number of presentations today about what other groups are doing with quantum, as well as what IBM is doing to make quantum possible. This is also an opportunity for StatsCan to position itself as a leader in quantum machine learning within the government by identifying opportunities early on in the development of quantum computing. So, we're all very excited about the opportunities, but we are familiar with the fact that is very new in this field, right? These applications in this field are very new and still developing. It's also in line with the recently announced national quantum strategy proposed in budget 2021 by the government of Canada. So there's funding available for government organizations to start looking into quantum applications for their own work. It's also a good idea to build partnerships with leaders in the field, like the University of Sherbrooke's Institut Quantique, as we're here today, also others within the government. And having your organization at the forefront of some of these technologies mitigates the risks of being disrupted by them. So, it's all great to take advice from people outside your organization, but it's even better to have people within your organization who have the expertise in order to apply this advice directly to your subject matter. So why would StatCan be interested in quantum? So anyone who's not familiar, Statistics Canada is Canada's national statistics organization. It's our job to provide high quality data about our population, the businesses who exist here, the workforce, everything like that, so that the government and the citizens can make informed decisions about what constitutes our country and our needs and our capabilities. So why would an organization like that be interested in quantum? Well, concretely, there's a few different classes of problems we've identified. The first is that of classification tasks. So StatsCan takes in huge amounts of data from all sorts of different sources, both from surveys, also admin data from different organizations, different companies, things like that. And this data is obviously massive, right? We've got a country of 33 million people, so anything to do with population is massive. Oftentimes we have to do classification tasks on this data. So for example, the problem we're going to talk about today is of product classification. So given a description of a product, let's classify it into what kind of product it is so that we can use it to compute statistics on different types of products, not just individual ones. These classification tasks often also have a hierarchical structure, which I'll talk about more in a second, but this structure gives us potentially even more opportunity to take advantage of quantum. There's also these more familiar optimization problems. So for example, while much of the census is computed online these days, there's still a lot of surveyors who go door to door and from business to business looking for survey respondents. Routing these census enumerators around is basically can be reduced to a graph traveling problem, like traveling salesman, with a few additional constraints. So these sorts of problems are common to all national statistics organizations and would have huge interest in speeding those up. There's also lots of potential opportunities that we have yet to explore. So we know that quantum computers can sample complex distributions much better than classical computers can. We do a lot of random sampling at StatsCan, things like item imputation, so replacing missing values in data sets with random data, such that it doesn't, the data we impute doesn't change things like the aggregates that we compute. or synthetic data generation. So sometimes we have data that's so sensitive, we can't allow it to be computed on directly outside of really strict compute settings. So if we can generate synthetic data with the same properties, but no privacy risks, we're better able to apply novel methods to these data sets. And then again, it's good to just have people in your organization who are familiar with potential for disruption, right? We've all heard about cryptography. Of course, we use cryptography. It'd be good to know upfront what sort of risks we have. We also have a lot of people at StatsCan who work on statistical disclosure control. So basically, when we release aggregates, we want to make sure that people aren't able to reverse engineer those aggregates to learn more about the input data than we want. So if we release some average about businesses and their outputs in a certain location, we don't want people to reverse engineer that to figure out what each individual businesses are, right? That's an example. The statistical disclosure control methods that we have in place are based on adversaries that exist today, classical adversaries. What kind of capabilities will quantum adversaries have? So let's go a little bit deeper into the two of the applications that we've mentioned. So the first is this hierarchical classification. So the North American product classification system is a system that classifies products across North America. It's got this hierarchical structure, as you can see. So it's a 7-digit code altogether, but it starts with a small group that you can then expand into and get more specific. So we go from crop products to different types of crops to specific products within that type of crop. While you can treat this as a classification task where you classify all these objects as different, right? These different types of grain, classify them as different things. You could also potentially use this hierarchical structure to say, well, things that exist in other crop products, they're different from live animals, right? So you can classify first live animals or crop products, and then within there, you can classify grains, oilseeds, or other, and then keep going deeper and deeper. And this potentially is someplace that has structure that's available that we haven't taken advantage of, that seems ripe for something to come in and help us. The other is this routing problem I mentioned. So these are, this is downtown Ottawa. These red marks are, red lines are follow road networks, and they demark different census blocks. So the respondents within these blocks are treated in different groups in the census. We need to route our surveyors from place to place, from block to block in the most efficient way possible, right? Efficient routes decrease costs, and they also increase the safety of surveyors, right? The less time they have to spend traveling, the less chance they have of any kind of injury or danger, and obviously that's the top priority. Current methods are very inefficient, so they can take up to on the order of multiple days to find suboptimal routes. And these routes also may need to be recomputed, so such as for non-response follow-up. So say a few of these blocks need to be revisited later on. We would like to recompute the route to make it most efficient again, but we won't be able to do that because it's so expensive to run. And this is a problem that exists across all NSOs, right? Every National Statistics Organization does surveys. Everyone needs to send surveyors around. No one has a better solution than this. So this is another thing, and this is really just traveling salesmen, right? With a few extra constraints that I won't get into. So how did StatCan get on the path to the quantum realm? Well, the first thing was identifying a use case with potential quantum advantage. And this is, I'll talk about the problem in a few minutes. It wasn't an obvious quantum candidate, right? It was kind of like a wild card. Identifying a problem that we had, it was not clear that there was a quantum solution, but let's look at it through a quantum lens and see if there's something that we can do that we can't do in the classical scenarios. In January 2021, we went to our research and development board and procured funding. They were very excited to fund a quantum project. This is the first step that we've taken as an organization into the quantum world. We partnered with Institut Quantique and worked very closely with both Fred and Sarah. So hello to both. We've been working with them, meeting weekly, since April. We started with a literature review, so took advantage of their expertise in the literature, worked together on data pre-processing. So how do we get this data first into a usable form, then how do we get it into a computer? And then we experimented with different methodologies, with some of which I'll talk about today. And we identified 3 different approaches to quantum machine learning. We benchmarked on simulators and we found that they showed potential. And in progress is testing these on real quantum devices through the IBM Q Hub. So a few of these have been run and have some interesting results, and I think there might even be some running as we speak. So let's talk about our use case then, which is quantum text classification. So this ties right back into this North American product classification system I talked a few minutes ago about. At StatCan, we have this data called scanner data, which comes from the business side of statistics. We get this data from retailers across the country, and it basically consists of product descriptions, some identifiers, and price of transactions. So scanner data, it's named after the price scanner guns that they use to ring you through checkout at retail stores, like grocery stores. These product descriptions are what the retailers use internally. So they don't have to be standardized by anything. They can vary wildly across different retailers and also wildly across different brands of the same product, right? So Heinz ketchup might be differently denoted from other brands of ketchup. We want to use this data to compute business statistics, particularly the consumer price index, which is a measure of the buying power of the Canadian dollar across the nation. So, one way to measure the buying power is how much does it cost to get a load of groceries or to buy this product or this product. The first step is to use machine learning to convert these product descriptions, which are, I said, very wildly, into this North American product classification system, right? So we want to put everything that is like sauces together, all together and treat them as one object. We want to treat all frozen desserts as one thing and treat them as one object. And of course, we're talking business statistics across the nation, so there's millions and millions of these transactions that happen. So we can't tag these by hand. We have to use machine learning. And once we use machine learning to get this classification system, we send it off to another team to do further analysis. They basically compute statistics on these values together with some of these identifiers. Not too important to us what they do with it. It just matters that we want to get as high an accuracy of this classification task as we can. So let's talk about one of the challenges, really. This is true with any text classification task. So recall, we're trying to put short sentences into codes. Typical data encodings for text problems are very high dimensional. So the kind of standard that we were using at StatsCan already for this task was tens of thousands of feature space. Tens of thousands features in the feature space. This is very high dimensional. This is way too large for a quantum computer, right? We need to encode this data into something closer to the order of 10 to 32 features, right? That's how many qubits are available on the machines we're running. But we need to do this while preserving the variance of the data. So this is a problem in text classification that makes it difficult to apply quantum methods, is this problem of encoding. Keeping the variance in the data, we know that text data, natural language data varies wildly, but we want to keep this variance. There's also some problems with multiple classes. I don't think we'll talk about that too much today. So let's go over a few of the frameworks we worked on. The first is kind of the standard, the variational quantum classifier. It's kind of your bread and butter quantum neural network. This is this, I think I saw this on a few slides earlier today, so I won't talk too much about it. But first, you encode your data as a quantum state, assemble some sort of circuit according to an ansatz that you create, and then you train your circuit similarly to how you train a classical neural network. And in fact, a lot of the work is done on a classical computer. We use the quantum circuit as kind of an oracle for running the neural network. And then we get a cost value, we put that through a classical optimization algorithm, we update our parameters, and then we run the quantum circuit again as a subroutine. And this is a purely quantum solution that's been shown to perform well with fewer tunable parameters than classical neural networks. But of course, the choice of the ANSAT, so the quantum circuit we put here, is pretty non-trivial and also non-intuitive. Next, kernel methods. So I think Paul mentioned kernel methods earlier today. This is kind of a new hot topic. The idea is that if you have a data set whose decision boundary is complicated and not easily parameterizable, we can kind of use kernel as a shortcut. So this, let's consider this data set here where we've got red X's separating blue X's. Say we want to separate this data with a linear, with a line. It's clear that there's no line that separates this data. But what we can do is embed this data into a higher dimensional space such that it is, the embedded data is separable by a linear subspace. So this hyperplane here nicely separates the red and the blue. And then we can drop this hyperplane back down into a lower dimension such that it still separates these values. The problem is that this process is expensive. Embedding data into a higher dimensional space is costly. Running this algorithm in the higher dimensional space is more costly than it would have been in the smaller one, and then dropping it down is costly again. What we can do is use something called a kernel function and do the kernel trick, which basically does this three-step process in one step. And the benefit of doing this in a quantum computer is that quantum circuits seem to be more expressible than classical circuits. So we can make this kernel be a lot more tunable and also more expressible and give us a better embedding. So again, we'll use a quantum kernel here, but we'll train it using classical methods that already exist, and hopefully we'll get something that works better. The last is transfer learning or hybrid learning. So the idea is we can combine classical and quantum machine learning methods. So transfer learning classically takes an algorithm that's been trained on a general task and fine-tunes it to your application-specific task. So you may take a network that's been trained on traffic data and use it to fine-tune to find specifically stop signs or something specific like that. This way we can take advantage of training done by tech giants with massive data sets to work on our more modest data sets. So for example, OpenAI's GPT-3 cost something like $12 million to train over 355 GPU years. Transfer learning allows us to put a quantum layer on top of that so that we're not competing with classical models, we're actually collaborating with them. So here's the idea. We take something that's been pre-trained, we chop off the end of it and put a quantum layer there, and then we train it a little bit more on our own task. And the idea here is that, yeah, again, cooperating with classical methods, we may be able to get something stronger than the classical methods by themselves or the quantum methods. Wrapping up, how can, so coming from someone who's recently helped walk their organization onto the quantum path, how can I advise you to get your organization on the quantum path? Well, the first is to enumerate potential use cases, no matter how wild. So for example, well, not for example, you know, the idea here is not to like become an expert in quantum and start to look at problems that quantum may help. The idea is to look at problems that you have existing and then try to find quantum solutions to them. So every organization has problems that they've been grappling with for a long time and just don't know how to solve. These are the sorts of problems that applying a creative quantum solution to have the most potential of an advantage, right? The benefit of platforms like IBM Q is that so many different people can try out so many different things that eventually the creativity of the masses are going to lead to breakthroughs in places where we may not expect it. Start building local expertise among your data scientists. So Stackhammer was lucky that they have a few data scientists who were trained in quantum. IBM Q and the quantum experience makes it really easy to get started with some of their online tutorials. Build partnerships as you go, right? This is a group effort, and the more eyes looking at a problem, the better. Begin experimenting with quantum simulators. Again, these exist. They're easy to work with, and You can iterate your solution as you go. And finally, you can run your candidates on real quantum hardware. Thank you everyone for listening. Merci pour votre attention. This project was in partnership with Institut Quantique and Bank of Canada. Special thanks to the rest of the team. Thank you for listening, and I'd be happy to answer any questions.
Well, great. Thanks very much, Zachary. It was it was a great project. It was great working with you, and I guess that you couldn't have expressed more clearly how an organization can jump in quantum computing. It's way clearer than the roadmap I proposed earlier today with a real example here. So, well, thanks a lot. That was great. Before we go to the break, well, let me switch back to French. So if you want to get the English translation, you can use the button. Alors, avant d'aller à la pause, laissez-moi répondre à une question qui vient de la section de questions et réponses dans le Zoom. Alors, la question est, avec les présentations qu'on vient de voir, la personne qui pose la question là, a le feeling que les membres du Hub ont probablement les mêmes types de challenges ou de mêmes types de défis qu'ils vont rencontrer en info quantique. La question, c'est est-ce que les membres peuvent se parler entre eux pour justement aller plus loin ou est-ce que ça passe nécessairement par l'équipe de programmation de la plateforme? Excellente question. En fait, il existe toutes sortes de façons de faire. Notre équipe de programmation rencontre régulièrement, on l'a mentionné tantôt là, avec Hudson, rencontre régulièrement l'équipe de programmation chez CMC Microsystèmes. On a un projet qui est aussi en train de démarrer avec Lockheed Martin. Donc, c'est clair qu'il y a ces rencontres-là qui se font. Puis, vous venez d'entendre Zachary avec le projet de Statistique Canada. Il y a quelques semaines, quelque chose comme 3 semaines maintenant, on a fait une première rencontre des membres du Hub. Donc, c'était une première fois où, effectivement, on assoyait tout le monde du côté scientifique, donc expertise scientifique pour discuter, voir un peu des problèmes. Comme c'était une première, je vous dirais, c'était une séance où on apprivoisait là, un peu le fonctionnement du Hub. Maintenant, on a l'intention de récidiver de ce côté-là. Donc, oui, continuer d'avoir des contacts réguliers avec chaque organisation, mais c'est clair que d'avoir des rencontres scientifiques pour discuter de ces questions-là, c'est aussi fondamental et ça fait partie, si vous vous rappelez, d'un des 3 axes de développement dont on parlait au début là, pour l'espace IBM Quantique, qui est la communauté. Donc, comment justement créer cette synergie-là entre les organisations. Donc, oui, utiliser le Hub, utiliser l'espace IBM Quantique comme catalyseur au centre de tout ça là, pour stimuler, évidemment, fluidifier les échanges et s'assurer qu'on est capable collectivement d'en apprendre le plus possible et d'aller le plus loin possible. Donc, excellente question. Effectivement, on met tout ça en place. Hein, vous le savez, ça fait 1 an et demi qu'on est en opération. Donc, à mesure que les projets arrivent, à mesure que les partenaires se joignent aussi à l'espace IBMQ, bien évidemment, on modifie nos façons de faire, on les améliore, toujours dans l'idée d'être le plus efficace possible dans tout ça. Donc, en parallèle, évidemment, il y a aussi toutes les sessions de formation, on en a parlé, donc nous, on en monte beaucoup. Il y en a qui sont aussi disponibles du côté du IBMQ Network. Donc, avec tout ça en place, on a un écosystème qui est croissant et florissant à Sherbrooke, plus largement au Québec, plus largement au Canada. Donc, tout ça, vraiment, tout en synergie. Donc, sur ce, on va prendre une pause. Donc, c'est la pause de 11h-3 officiellement. Et on revient à 11h15 pour la suite. Donc, on revient avec la présentation des projets, je vous dirais, plus interne ici à l'Université de Sherbrooke. Donc, on va vous présenter ce qui s'est passé là, dans les derniers mois, dans la dernière année également. Donc, on se revoit dans 17 minutes à 11h15. Merci beaucoup tout le monde. Alors, bonjour tout le monde. J'espère que vous avez eu le temps d'aller chercher votre café. Notre prochain invité, Stéphanos Courtis, est directeur de la plateforme de calcul quantique à l'Institut Quantique. Plateforme de calcul quantique qui est la structure qui englobe l'espace IBM Quantique. Et donc, son directeur, Stéphanos Courtis, c'est notre prochain invité qui va venir vous adresser la parole. Donc, Stéphanos, je te laisse te présenter, mais aussi présenter les travaux de recherche que tu fais dans ton groupe, voir comment justement vous orienter votre pratique là, vers l'info quantique. Donc, Stéphanos, à toi la parole.
Merci beaucoup, Ghislain. Bonjour tout le monde. So let me share my screen with you. Okay. So today I would like to, first of all, I would like to welcome everybody. It's very nice to have everybody participate in this event. For this presentation, I will take off my director hat and instead put on my researcher hat and also the hat of a user of the plateforme de calcul quantique at Institut Quantique. And I will tell you what my research group has been doing in the last year and a half that I have been here in Sherbrooke. So we call our group the Quantum Information and Computational Physics Theory Lab, or QUICOFI Lab for short. So our research focuses on the fundamental, right? We do fundamental research into quantum many-body systems, entangled systems, and we try to get to the bottom of fundamental properties. But apart from this, we like to make fundamentals dance, okay? So it's not just the fundamentals that we are interested in themselves. We also have an eye out for how these fundamentals can be used. Okay, so who is the lab? It's these wonderful people. We have postdocs, PhD students, and master's students in the group. It's a great privilege to be able to work with these people. And I will tell you very briefly, I will show you what we have been working on. Obviously, everything that I will be discussing is work in progress, except for some highlights that I will show you in a second of work that has been completed recently. Okay, so our funding comes from all these organizations, which we gratefully acknowledge. So both in the university, in the province, and on the federal level. So a little bit about the background, my background. So I'm a quantum many-body theorist by training. I grew up scientifically studying strongly correlated electron systems. And so that is also part of what we do today. And in particular, we are interested in systems that are not regular, in a sense that they are not, they don't form regular patterns. The degrees of freedom do not form regular patterns, so they are disordered. Furthermore, I am interested in quantum dynamics, meaning how quantum systems evolve in time. Which is can be something that ranges from very close to how a classical system evolves to something completely different, and even exhibiting properties that are chaotic, or exhibiting signatures of quantum chaos. And moreover, I am also interested in computational physics, meaning to develop algorithms for how to simulate all these systems. So methods like sparse eigensolvers, tensor network methods, Monte Carlo methods, etc. Okay, so this is the expertise, and so we come with this expertise into quantum computing and quantum information. And it's, I think, precisely because of this varied expertise from myself and within the group that we have a good shot at solving actual problems. Okay, because one of the things that is so great about the field of quantum computation and quantum information is that it really requires an interdisciplinary mindset. And this is why we are in a great advantage here at Institut Quantique in Sherbrooke, because we embrace this interdisciplinarity as a core value. So this is an overview of the research program that's actually ongoing in my group. It's split into two big categories. The first one is near-term quantum and quantum-inspired computation, which perhaps will interest this group more. And the second one is computational quantum matter. In the first research area, we have three main interests currently. The first one is directly related to the Espace IBM here at Sherbrooke, which is how to domesticate NISQ calculators. NISQ means near-term intermediate scale quantum calculators in this case, and I call them calculators because as you have seen before, the name of the game is finding purpose-built or purpose targeted applications for these machines. And so we are working on projects related to combinatorial optimization, combinatorial enumeration, counting, etc. And also we are starting to dip our toes into quantum machine learning and quantum kernel methods. Another direction that's currently big in the group is quantum error correction, both on the decoding side, meaning the characterization of quantum error correcting codes, which are the tools that will allow us to go beyond the NISQ era into full quantum computation in a few years' time. And also how to design quantum error correcting codes such that they work with various restrictions on hardware, etc. And finally, is what I call quantum-inspired problem solving, which is basically, since we have experience in solving problems in the quantum domain, and we have gotten quite good at it, then perhaps we can use this intuition to solve problems that are in different domains. Okay, and this involves taking methods that were developed for quantum problems and repurposing them to solve other problems. And I will show you an example in a bit on how we use tensor network algorithms that we repurpose from doing something quantum to doing something not quantum. And then the second category, computational quantum matter, we are interested in highly entangled systems, highly entangled quantum states, how they arise, the potential for them to arise in quantum materials that are driven out of equilibrium, and also in quantum simulation, and particularly how to simulate systems that are hard to simulate otherwise, both quantum and classical. Okay, so just to give you an idea, in the domesticating NISQ calculators, we have two postdocs, Roya Radkohar and Shreya Banerjee, who are working on this. Quantum error correction, we have Sam de Rosier, Maxime Tremblay, Alex Berezutsky. Am I forgetting someone? Yeah, Nueddin Baspin, who's actually just graduated. Quantum-inspired problem solving is basically something that we are all working on all the time, but particularly I am interested in. In the highly entangled quantum matter, we have Martin Schneer, who is actually working on a model of a particular structure that can be made, devices that can be made in the lab, and they are envisioned as quantum simulators with trapped ions. And in the quantum simulation, Jérémy Gauthier, who's a student, a PhD student in the group, currently simulating spin glass systems using the IBM Q computers. Okay, this is just an overview of what is ongoing. There's other things that are coming. Omar Shikar, who is also an intern, has also started now a master's in joint supervision with me and Guillaume Rabusseau, who's a professor at Mila, and we are going to do quantum machine learning, quantum kernel methods, as I mentioned before, after he's done with his courses. Okay, so let me give you just one taste of one of the things that we have recently published, which has to do with the classical simulation of quantum computers, because the frontier of quantum computation today is defined by how fast we can simulate quantum computation. And in this paper, which was published earlier this year, a collaborator and myself showed that, in fact, we can simulate quantum algorithms or quantum algorithms run on quantum circuits much faster than was expected before by using a technique called tensor networks. And here in these graphs, you see the number of gate layers that the quantum computer runs versus the simulation, classical simulation costs on the y-axis. And what you're supposed to see is that these curves go down if you use better methods. And so you end up being able to simulate them. So here I'm showing a random circuit sampling task and also a variational quantum algorithm called quantum approximate optimization. And so basically we can simulate up to thousands of qubits easily for this algorithm. So this was also featured in this summer in the Google Quantum Summer Symposium by Hartmut Neven, who is the engineering director at Google Quantum AI. And so, of course, here there's Google needs a bit of classical error correction also, but basically they mentioned these methods as the most advanced techniques for actually ascertaining a quantum advantage, right? So we hold basically the frontier currently. And in this slide, the claim was that the experiment was not simulated yet. Classically, the Google experiment that claimed quantum supremacy, actually, in the meantime, the precise circuits that Google ran have been simulated using our methods. So the tensor network methods are a technique that comes from quantum many-body physics, but in fact, you can repurpose these techniques to solve problems that are of actual interest in computation in general, beyond just simulating quantum computations. And here I'm showing some examples from various papers where we tackle hard combinatorial optimization or combinatorial enumeration problems like graph covering, counting graph coverings, weighted model counting, or calculating knot invariants, or more simply, calculating how to untie your shoelaces when they're very, very tangled. Okay, and in all these cases, we show that we can, using inspiration from quantum, we can solve problems with a performance equal or better than the state-of-the-art algorithms, okay? So here is another highlight. Recently, there was the GTC AI conference of NVIDIA, and the director of engineering over at the Math and Computing, Quantum Computing Libraries at NVIDIA presented their newest commercial library that they're launching called QTensorNet. And if really tiny here on the slide, you will see that basically the techniques that they are using, they're implementing on a commercial level are actually our methods, okay? So for me, just to give you like a personal point of view, I have never, even though I worked on quantum things before, I have never seen such a fast adaptation and such a fast moving field where we come up with the algorithms in 2020, or maybe in 2019 in this case, and they are actually implemented commercially in 2021, within 2 years' time, okay? So this is extremely fast from like fundamental to applied. And also just as another data point is, in this work that I recently noticed, the author actually uses our methods for a completely different field that we had not even imagined when we were actually developing these methods. Okay, so and actually I don't even know what exactly this is used for, but actually it is useful beyond the original intentions. Okay, so in fact we have quantum inspired methods that lead to even classical algorithms that improve people's lives from the computational standpoint. Okay. For what's coming, as I mentioned, we have a number of things that we are working on currently. Our focuses will be quantum kernel learning, as I mentioned, with in collaboration with Professor Abusseau over at Mila. Quantum error correction, of course, will be a big thing for us in 2021, 2022. And also continuing to develop near-term quantum computation simulation algorithms, as I discussed before. Throughout all this research, we have the wonderful support of all the quantum devs and the team at Espace IBMQ, and so this is something that permits us to imagine things beyond the say the daily theoretical quantum condensed matter physics toolbox. Okay, so this is something really cool that even if we just have it in the back of our heads, that we can use these things actually helps us think in a different way. And so before closing, I wanted to tell you what the true quantum advantage, for me at least, has been since I arrived here, and it is precisely the people. As Ghislain said, the people that come out of our training programs are the quantum advantage, the true quantum advantage. And in my case also, it's a quantum advantage that I benefit from every day.
Great, thank you, Stefanos. There's a few questions for you in the chat. If I start with the first one, can you develop a little on the quantum advantage regarding Monte Carlo simulations or general random process modelization?
Yeah, so we are not aiming to get a quantum advantage specifically on Markov chains or anything like this, but random sampling, for example, or how to do approximate counting, how to do approximate sampling. All these things are things that we are interested in and currently exploring. The idea is to somehow explore space, a combinatorial space, as fast as possible, using a random walk within this space on a quantum computer, and then try and sample from it. Okay, of course, the details on how to do it exactly to obtain an advantage, I cannot get into too much detail, but there are generic advantages that one can get by virtue of using such techniques. And that's the type of advantage that we are interested in exploiting. But perhaps something that might interest people more is that beyond just proving a theorem, sometimes the overheads of, say, a Grover type algorithm, a Shor type algorithm running on these machines is so significant that you can actually not try them. So one of the things that we are interested in is quick and dirty algorithms that you can use to get answers now, with hopefully with some guarantee on the quality of the answers that you get. Okay.
Okay, well, thanks. And well, the next question actually is twofold. The first part is, are quantum algorithms theoretically better suited for chaotic system analysis? And the second part, and do you think superposition can get rid of the precision error due to the finite nature of classical computing?
So can you repeat the first question?
Yeah. Are quantum algorithms theoretically better suited for chaotic system analysis?
If we are talking about quantum chaos, then yes, because it is much more natural to simulate a quantum system with another quantum system, and of course, much more efficient if you do it the right way. For the second question, which was regarding the finite, what was it? Finite nature of
classical computing.
Yeah, I'm not sure I understand the question. So the person who asked the question, they should contact me and we can discuss it.
Okay, great. So now the invitation has been launched. Well, thank you very much, Stefanos, for your presentation. Very interesting to see what you're working on, and well, hopefully having you next year for well, knowing a bit more about what the results will be like in the next in the next steps for you and your group. Well, thanks a lot. On that, we will go with Aiki Russolo-Manana, who worked with us last summer as an intern at the IBM Q Hub. Donc, Aiki, en fait, si tu veux poursuivre donc la discussion et nous raconter donc comment s'est passé ton stage et puis peut-être aussi sur quoi tu as travaillé là, pendant les semaines que tu as passées avec nous l'été dernier. Donc, à toi la parole.
Ok, merci Ghislain. Bonjour à tous. Moi, je m'appelle Aiki, je suis étudiant aujourd'hui à Montréal, à l'Université de Concordia, et j'ai eu la chance de faire mon stage en informatique quantique l'été passé à l'espace IBM Q. Et aujourd'hui, j'ai l'honneur de vous en parler. Alors, ma présentation s'articulera en fait sur 3 axes. Premièrement, je vais vous parler vite fait de comment je me suis retrouvé comme ça stagiaire à l'espace IBM Q. Puis, je vais bien évidemment vous parler de mon projet de stage qui portait sur la coloration de graphes. Et enfin, je vais faire une petite aparté sur ce que le stage m'a apporté moi personnellement en tant qu'étudiant notamment. Alors, j'ai toujours été un fan de physique, fan de sciences et je regardais et je regarde encore beaucoup de vidéos, beaucoup d'articles qui portent sur la science, la physique. Et puis, vers les années 2016-2017, je suis comme ça tombé un petit peu par hasard sur pas mal de contenus qui parlaient d'informatique quantique. Moi, ça m'a fasciné, j'étais très vite intrigué. Bon, à l'époque, j'étais encore au secondaire, je ne comprenais pas grand-chose. Et en fait, même si je comprenais un petit peu dans la globalité comment ça fonctionnait, moi, dans le détail, je ne comprenais pas grand-chose. Et c'est cette incompréhension du détail, en fait, qui s'est tournée en intrigue, puis en curiosité. Et donc, j'ai commencé mon bac en physique avec comme ça l'idée au fond de ma tête de dire, OK, un jour, j'étudierai l'informatique quantique, regarder un peu plus dans le détail ces machines fascinantes. Et c'est là notamment qu'intervient l'espace IBM Q, que j'ai rencontré l'an passé, un événement organisé par l'Université de McGill, le Physics Hackathon. C'est là où j'ai rencontré Ghislain Lefebvre et je lui ai très vite énoncé mon intérêt pour l'informatique quantique et notamment mon désir de faire un stage dans le domaine. Et les choses, en fait, se sont passées très, très vite, puisqu'au bout de quelques jours à peine, je rencontrais mon futur tuteur de stage, Maxime Dion, que je salue au passage si jamais il m'écoute. On a parlé de mes connaissances, ce que je voulais faire, etc. Et puis, les semaines passent, les procédures administratives se font, et puis, en fait, me voilà un beau jour, au mois de mai, au sein d'une très belle équipe pour aller travailler en informatique quantique. Alors, durant ce stage, je n'ai pas chômé puisque j'ai travaillé sur ce qu'on appelle la coloration de graphes. Alors, vite fait, qu'est-ce qu'un graphe? C'est tout simplement un ensemble de points qu'on appelle les sommets. Et ces sommets sont connectés entre eux par des arêtes. Typiquement, n'importe quelle figure géométrique, polygone par exemple, c'est un graphe, un rectangle, un triangle, un hexagone, etc. Mais en pratique, vous pouvez avoir des graphes bien plus complexes, bien plus larges qu'un simple carré, comme vous voyez à l'image. Le problème sur lequel je me suis attardé durant tout l'été, c'est le problème de la coloration de graphes. C'est un problème très facile à énumérer et très facile à comprendre, vous allez voir. Vous prenez un graphe et l'objectif, c'est tout simplement de colorier tous les sommets avec des couleurs différentes. Alors, dans le cadre du stage, dans le cadre de cette présentation, je me suis focalisé sur 4 couleurs, mais vous pouvez avoir différents nombres de couleurs en fonction des graphes que vous avez. Donc, je disais Le but, c'est de colorier tous les sommets du graphe, mais il y a une contrainte, une seule et unique contrainte. Quand deux sommets sont connectés entre eux, ces sommets-là ne peuvent pas avoir la même couleur. Donc, vous voyez à l'image à gauche, un carré tout bleu, ça ne correspond pas à la contrainte, tandis que le carré de droite répond correctement au problème. Avant d'aller chercher à résoudre ce problème en question, il est important de le modéliser. Et c'est là où j'introduis la notion de fonction de coût. Alors derrière ce nom un petit peu barbare se cache en fait un concept assez simple à comprendre. Typiquement, vous prenez une paire de sommets connectés et à ces paires-là, vous allez donner une valeur. Lorsque les paires sont correctement coloriées, c'est-à-dire que les sommets ont des couleurs différentes, comme ici à droite, vous allez donner à cette paire une valeur de 0. Si la paire n'est pas correctement coloriée, c'est-à-dire que les sommets ont une même couleur, comme ici à gauche, bleu et bleu, alors vous donnez à cette paire une valeur de 1. Vous pouvez penser un petit peu comme si c'était une pénalité. Parce que tu n'as pas respecté la contrainte, alors je te donne une charge plus importante à soulever. Vous faites ça pour toutes les paires qui existent dans votre graphe et vous faites la somme. Vous obtenez une valeur totale, le coût total associé au graphe. Typiquement, à droite, vous voyez que si le graphe est correctement colorié, vous obtenez un coût total de 0, c'est la valeur minimale. Et si le graphe n'est pas correctement colorié, vous obtenez des valeurs supérieures à 0, 1, 2, 3 ou 4 étant le maximum pour le carré ici présent. Donc, vous voyez que en fait, le but du jeu, finalement, ce n'est plus tellement d'aller chercher à colorier des sommets, mais c'est plus à aller trouver la configuration qui a le coût minimal. Comment est-ce qu'on fait ça en pratique? C'est assez simple à expliquer, un petit peu plus difficile à mettre en place. Prenez votre graphe, vous prenez chaque sommet du graphe et vous associez à ce graphe un qubit. Un sommet égale un qubit, et il est important de préciser qu'en fait, l'état du qubit déterminera la couleur associée au sommet en question. Parce que vous avez introduit la notion de qubit, en fait, votre graphe finalement est associé ou devient un état quantique. Et cet état quantique dépend de plusieurs paramètres variables. C'est-à-dire qu'en fait, l'état quantique ou l'état d'un qubit va dépendre de plusieurs nombres. Et ces nombres-là, en fait, vous pouvez jouer avec pour obtenir différents états. Et en fait, le but du jeu, finalement, c'est d'aller jouer sur ces paramètres-là. Comment on fait? Je reviens sur l'état quantique. Cet état quantique est en fait modélisé par l'ordinateur quantique lui-même. Lorsque j'ai modélisé cet état quantique, en fait, je fais une mesure à la fin, une mesure de l'état quantique où j'obtiens un nombre. Ce nombre, ce n'est ni plus ni moins que le coût du graphe. Et l'idée maintenant, c'est qu'on va aller chercher avec un ordinateur classique les paramètres qui vont aller dans la direction qui minimise le coût associé au graphe. Donc l'ordinateur classique comme ça va aller chercher un peu comme si vous étiez à la montagne dans une voiture, et pour aller descendre, vous prenez la route comme ça qui va mener vers le creux de la montagne. Et c'est exactement ce que fait l'ordinateur classique. Il va générer des nouveaux paramètres dans cette direction-là, et ces nouveaux paramètres, on les réinjecte dans l'ordinateur quantique, et on fait comme ça, on continue la boucle jusqu'à ce qu'on obtienne la valeur minimale, le coût minimum associé au graphe. Et ce coût minimum-là sera effectivement la solution au problème donné. Alors, si colorier des graphes peut paraître un petit peu anodin, un petit peu ennuyant pour certains, et je le concède, en fait, en réalité, c'est un problème très vaste, parce qu'en fait, il répond à beaucoup de contraintes qui existent notamment dans les transports, dans les logistiques. En fait, tout ce qui est lié à la planification, notamment des avions, des voitures, des trains, c'est modélisé avec le problème de la coloration de graphes. Pareil, au niveau de la télécommunication, comment vous allez mettre les antennes, notamment les antennes 5G par exemple, pour parler d'actualité, comment vous allez les agencer dans votre ville, c'est aussi un problème lié à la coloration de graphes. Et en fait, en général, n'importe quel problème d'optimisation peut être décrit avec ce problème-là. Pour finir, j'aimerais étendre un petit peu mon propos sur ce que ce stage m'a apporté. Moi, cette partie ne sera pas fournie d'images, ce sera juste moi qui parlerai. Déjà, pour être honnête, et même si ça paraît un petit peu cliché, mais c'est la vérité, j'ai appris énormément de choses durant ce stage, aussi bien en maths, en physique, en informatique, et quantique et classique. J'ai découvert pas mal de notions ou redécouvert des notions durant tout l'été que j'ai pu un petit peu approfondir. Et ces notions-là, en fait, je les réutilise aujourd'hui dans mes cours actuels. Et c'est vraiment c'est vraiment plaisant parce qu'en fait, j'arrive dans mes cours avec beaucoup plus de sérénité, moins de difficultés. Et par rapport à quelqu'un, par exemple, qui n'aurait pas eu la chance de voir ou revoir ces notions-là, je pense notamment aux notions en mécanique quantique. Puis, plus particulièrement, ce stage, en fait, dans ce stage, j'ai eu une expérience humaine incroyable. J'ai évolué au sein d'une équipe de passionnés, une équipe passionnante. J'ai appris tous les jours, j'ai rigolé tous les jours. C'est une expérience inoubliable pour moi sur le plan humain. Et puis pour finir, en fait, ce stage m'a permis aussi d'avoir une vision un peu plus claire sur le futur, dans le sens où pour moi maintenant, l'informatique quantique correspond à une potentielle voie d'orientation après mon baccalauréat en physique. Et le fait d'avoir une vision plus claire comme ça me donne beaucoup plus de motivation pour la suite, mais aussi pour le moment actuel. Et pour les étudiants qui me regardent, ou les anciens étudiants, ou peut-être même les futurs étudiants, vous savez sans doute qu'être étudiant, il en faut de la motivation. C'est sur ces mots que je finis ma présentation. Je remercie l'espace IBMQ de m'avoir invité, d'avoir accepté de me prendre en stage durant l'été, et je remercie bien évidemment toute l'audience aujourd'hui qui m'a regardé.
Aiki, merci beaucoup. Ça a été un plaisir de t'avoir avec nous l'été dernier. Puis écoute, je regarde notre canal Slack à l'équipe actuellement. Tout le monde s'enflamme dans l'équipe, te salue et a fait transpérer que tout le monde a eu énormément de plaisir à t'avoir parmi nous. Donc, merci à toi. Merci pour ta présentation. Maintenant, pour ce dernier segment de la matinée, j'invite Sarah Blanchette, donc Sarah qui est avec nous depuis quoi, 6 mois maintenant, un peu plus, que tu t'es joint à l'équipe, oui. Hein? Et tu as été celle qui a été responsable, en fait, de la majorité des ateliers qu'on a donnés dans les cégeps cet automne. Donc, écoute, je te passe la parole pour ce segment, donc éducation côté préuniversitaire, puis voir un peu comment ça s'est détaillé tout ça là, dans les derniers mois. Donc, à toi la parole.
Merci, Ghislain. Puis bonjour à qui, c'est le fun de t'avoir vu. OK, donc aujourd'hui, je vais parler un petit peu de nos efforts de vulgarisation quantique qu'on a ici à l'espace IBMQ. Donc, je vais ramener l'image que Ghislain a présentée tout à l'heure. Dans l'espace IBM Quantique, on a 3 axes principaux. Donc, on a la recherche, la communauté et on a évidemment la formation. Donc, au même titre que la recherche, la communauté, la formation, c'est quelque chose qui est clé pour nous. Puis comme Danny tantôt l'a dit de chez Lockheed Martin, la formation, c'est un aussi grand défi, puis c'est aussi important que la recherche. Donc, en quantique, c'est super important d'avoir la relève. Et en fait, j'ai 3 citations ici que j'ai tirées pour un peu justifier pourquoi on passe du temps à bâtir du contenu, à le donner, pourquoi c'est une priorité pour nous de faire de la formation. Fait que, comme tantôt Zachary l'a dit chez Statistique Canada, on le sait, le budget fédéral 2021 a dit avoir investi près de 400 millions de dollars pour une stratégie nationale, je vois qu'il manque une stratégie nationale quantique, entre autres pour développer et pour amplifier le talent qu'on a ici au Canada, pour le former aussi. Il y a un rapport du CNRC, donc du Conseil national de recherche du Canada de 2019, qui dit que d'ici 2040, le domaine du quantique va offrir plus de 200 000 emplois. C'est vraiment beaucoup d'emplois à les combler, c'est beaucoup de talents à former. Et finalement, j'ai sorti aussi une citation d'un rapport d'IBM de 2021 qui, en fait, dit que si le Canada veut devenir chef de file mondial en informatique quantique, c'est une priorité vraiment de former le talent, de le garder, d'avoir des ingénieurs et des scientifiques, des programmeurs qualifiés. Donc, toutes les citations disent un peu la même chose. Le message vraiment, c'est qu'on a besoin de main-d'œuvre et de relève. Le quantique, il reste encore énormément de défis à relever, il reste beaucoup de recherches et il faut évidemment du monde pour faire ça. Donc ça, en fait, ça vient un petit peu justifier pourquoi c'est important de faire de la formation. Maintenant, c'est quoi la formation qu'on fait? Donc, quels sont les ateliers qu'on donne? Donc, on a 3 ateliers d'introduction. Donc, on en a un qui porte sur l'intro à l'informatique quantique, un second sur l'introduction à la programmation quantique et un 3e qui porte sur l'algèbre binaire, donc sur les maths derrière le calcul quantique. Ces 3 ateliers-là, on assume peu ou pas de connaissances en mathématiques, en physique et en programmation. Donc, c'est vraiment grand public. Puis ça, je vais y revenir. Et on a aussi 3 ateliers qui sont plus intermédiaires. Donc, on en a un sur l'optimisation quantique, plus spécifiquement sur l'algorithme QAOA. On en a un second sur l'apprentissage machine quantique, ou QML, donc Quantum Machine Learning en anglais, où est-ce qu'on fait de la classification, donc c'est une tâche super commune en apprentissage machine classique et quantique. Et finalement, on a un workshop sur la chimie quantique. Donc ça, c'est nos 6 ateliers, donc 3 d'introduction et 3 intermédiaires. Je veux faire un petit survol rapide du contenu qu'on a dans les ateliers d'introduction parce que j'ai réalisé que c'est peut-être pas super clair. Qu'est-ce que ça veut dire un atelier d'introduction sur l'informatique quantique? Qu'est-ce qu'on voit dans un atelier comme ça? Donc, on voit évidemment de la mécanique quantique. Donc, on va voir des principes importants comme la superposition, l'intrication, le parallélisme. Mais encore une fois, je le rappelle, sans se noyer dans les mathématiques parce qu'on n'assume pas de connaissances en mathématiques. C'est très rare d'avoir de la mécanique quantique qui est un cours universitaire, qui se fait sans mathématiques avec peu de connaissances en physique. Fait qu'on voit évidemment la mécanique quantique. On vient aussi parler des qubits, mais du côté aussi c'est quoi les architectures des qubits? Donc, physiquement, qu'est-ce qu'un qubit? C'est quoi les différentes architectures qui existent? Excusez-moi. Donc, on a par exemple ici les qubits superconducteurs et les qubits de spin. Donc, 2 types de qubits qui sont beaucoup étudiés à l'Université de Sherbrooke. Fait que ça, on parle physiquement qu'est-ce qu'un qubit. Et on vient aussi, on vient programmer aussi les ordinateurs quantiques. Et comme je l'ai dit, on n'assume pas de connaissances pour les ateliers de base en programmation. Et par chance, IBM a une interface qui est super plaisante pour faire ça. Donc, c'est le Circuit Composer. Et là, en fait, on peut venir vraiment programmer un ordi quantique en glissant des différentes portes sur un circuit. Donc, on vient évidemment expliquer les concepts de porte, le concept de la mesure. Ici, on a un circuit de téléportation qu'on fait en long et en large dans la présentation. Donc, on peut venir avec ce circuit-là, c'est de le lancer sur une vraie machine. Et là, ça me mène un peu à l'image que j'ai à droite. Donc, nos ateliers sont évidemment interactifs. Donc, on invite toujours les participants à se faire un compte sur le site d'IBM Q et ça leur permet de lancer des calculs sur les machines. Donc, pour plusieurs, c'est vraiment une découverte de savoir qu'à partir d'un laptop personnel, on peut envoyer des calculs sur une vraie machine quantique à travers le cloud. C'est toujours le fun de voir la réaction des étudiants quand on leur dit qu'on va faire ça parce que c'est choquant pour plusieurs. Ça, c'est la programmation quantique. Mais on ne parle pas juste de la science et de la programmation, on vient aussi parler de c'est quoi les applications puis c'est qui fait du quantique. Et moi, je trouve que ça vient un peu rajouter de la valeur à notre présentation de dire c'est qui les joueurs, à quoi ça sert et comment on s'en sert. Donc là, ici, j'ai mis 2 entreprises en démarrage qui sortent de l'IQ à Sherbrooke, en fait. Et je pense que pour les étudiants, ça vient un peu concrétiser la science qu'on leur explique. Souvent, quand on fait de la science à un niveau comme ça, on n'est pas trop sûr où est-ce que ça sert. Et je pense que c'est important pour nous de vraiment passer le message qu'il y a Google, il y a IBM, il y a les gros joueurs, mais il y a aussi plusieurs startups qui sont là en quantique puis qu'il y a beaucoup de travail à faire encore. Ça leur donne un petit peu aussi une idée de c'est quoi les possibilités qui existent s'ils veulent poursuivre en quantique. Je vais parler maintenant de ce qu'on a fait dans la dernière année. Donc, c'est les nombres qu'on a réussi à atteindre. Donc, je vais commencer en haut par les cégeps. À l'automne, on a fait 5 cégeps où est-ce qu'on a donné les ateliers d'introduction à l'informatique quantique et à la programmation quantique. Et on a réussi à avoir plus de 300 participants, ce qui est vraiment énorme. On a aussi des ateliers qu'on donne au CMAI, donc à l'Institut pour la mobilité et l'aérospatiale au Canada. Donc, eux, en fait, une partie de leur mission, c'est de donner des séminaires, en fait, de rendre des séminaires accessibles à des jeunes du cégep et des études du premier cycle, donc du baccalauréat. Et ça aussi, on a donné encore des ateliers d'introduction ainsi que l'atelier d'optimisation. Encore une fois, on a eu plus de 300 participants au courant de l'automne et de l'été à ces ateliers-là. On a aussi QSATEC et Quantum BC. Donc, en fait, ça, c'est des programmes de formation qui sont adaptés au milieu d'emploi en technologie quantique. C'est pour les étudiants gradués et ça leur offre accès à différentes formations. L'année passée, en fait, à l'hiver passé, on a pu faire un atelier sur 3 semaines qui portait sur la chimie quantique. Et cet été, lors d'une école d'été, on a fait un atelier sur le QML. On a aussi eu la chance cet été de participer à un séminaire sur l'informatique quantique qui avait été organisé par l'École de la fonction publique du Canada. Et on avait un panel de discussion avec des gens d'IBM et de l'espace IBM Q, donc il y avait Ghislain et moi qui étions là. Et on avait près de 1500 personnes qui ont participé, donc c'est vraiment énorme, là. Et on avait aussi donné l'après-midi un atelier sur le QML avec, encore une fois, plus de 300 participants. Donc, on voit, somme toute, qu'on a réussi à rejoindre quand même un gros groupe de gens. Mais ce que je voulais faire ressortir avec la diapo, c'est qu'on a du monde du cégep, du bac, des études graduées et même du monde du milieu du travail, du marché du travail. Fait que ça couvre là, vraiment un public très, très grand. C'est super pertinent de faire ça parce qu'on le sait qu'avec des gens avec des différents backgrounds, des différentes expériences, connaissances, quand on vient ensemble, après ça, on peut faire de la belle recherche. On peut développer des belles affaires en travaillant ensemble. J'aimerais maintenant un peu, j'ai trouvé ça pertinent de parler du retour des étudiants. Donc là, j'ai justifié pourquoi c'est important pour nous de faire la formation, mais j'ai aussi, après les cégeps, en fait, on envoie un formulaire d'évaluation où est-ce que les étudiants nous disent leurs commentaires. Et j'ai passé au travers des réponses, il y en avait plus d'une centaine. Et j'ai pu faire ressortir un peu 4 points principaux qui peuvent un peu résumer c'est quoi les commentaires qu'on a eus des étudiants. Donc, évidemment, il y en a plusieurs qui ont dit avoir beaucoup apprécié le sujet. Et on parle d'intrication, de superposition, c'est des phénomènes qu'on n'entend pas parler beaucoup, mais qui sont vraiment tripants. Je pense que les gens apprécient beaucoup ça. Mais deuxièmement, pour plusieurs personnes, c'était une première introduction à un domaine qu'ils ne connaissaient pas du tout. Fait que ça, c'est quand même intéressant parce que le quantique, on le sait que ça va prendre de plus en plus de place. Donc, d'avoir eu cette première introduction-là, c'est super pertinent. Même s'ils ne vont pas continuer en quantique, au moins d'avoir une idée de qu'est-ce que c'est et à quoi ça sert, c'est motivant. Troisièmement, on a quelques étudiants qui ont mentionné que ça leur a donné la motivation de poursuivre dans le domaine. Fait que ça, c'est toujours plaisant à lire que les ateliers, ça a un peu comme je lis ici, que ça a concrétisé l'intérêt de certains étudiants de poursuivre en quantique, que ce soit en chimie, en physique, en génie ou en sciences quantiques à l'université, mais pour aboutir en quantique. Et finalement, pour plusieurs, ça a été une réalisation que c'est un domaine qui est plus accessible que prévu. Ça me rejoint beaucoup parce que quand j'avais découvert le site d'IBM Cube il y a quelques années durant mes études, je suis tombée par hasard sur le site d'IBM Cube et j'ai découvert c'était quoi l'informatique quantique. Je ne connaissais rien là-dessus. Puis j'avais vraiment aucune idée c'était quoi les possibilités d'emploi, qui faisait du quantique. Je pensais honnêtement que c'était un domaine qui était comme super inaccessible. Et là, aujourd'hui, je suis programmeuse, fait que c'est quand même fou. Mais c'est pour ça que je suis très contente dans les cégeps pour pouvoir montrer aux jeunes que c'est moins inaccessible qu'on peut le penser. En fait, ça mène à ma conclusion. J'aimerais juste conclure en disant que j'ai été super contente d'aller dans les cégeps cet automne. Vraiment, ce fut vraiment un réel bonheur. D'une part, d'avoir interagi avec les étudiants puis de répondre à leurs questions. Ça a été très le fun. Mais aussi, sur une note plus personnelle, moi, je réalise beaucoup l'importance des ateliers et des conférences durant le cégep. Donc, à cette étape-là du parcours scolaire, c'est vraiment crucial d'avoir des ateliers comme ça. Moi, lors de mon cégep, j'avais assisté à une conférence qui avait été organisée par mon cégep, qui avait reçu une professeure du département de physique de l'Université de Montréal. Elle était venue parler de sa recherche sur les trous noirs supermassifs. Et c'est un sujet qui était évidemment super intéressant. Mais elle avait aussi parlé du milieu académique de la physique, des débouchés qui existent en physique. Puis moi, je ne connaissais pas du tout ce domaine-là. J'aimais la physique, mais je ne connaissais vraiment pas c'est quoi les possibilités d'étudier en physique. Et je me suis beaucoup identifiée à la professeure. Et puis en fait, je dis souvent que c'est grâce à la conférence que j'ai vraiment décidé d'aller en physique puis de poursuivre mes études là-dedans. Fait que pour moi, d'avoir été dans les cégeps, j'ai trouvé ça, je me sens vraiment privilégiée parce que j'ai espéré avoir un impact comme elle a eu sur moi, sur les étudiants, pour un peu leur montrer qu'eux aussi ont leur place dans un domaine que peut-être ils ne pensaient pas qu'ils pourraient poursuivre dedans. Fait que sur ça, c'est tout.
Bien, merci beaucoup, Sarah. Puis, dans le fond, cet automne, donc, tu as été beaucoup dans les cégeps, tu as été dans d'autres activités aussi là, pour présenter les ateliers d'introduction. Et comme il a été mentionné plus tôt, tu as énormément travaillé sur le projet avec Statistique Canada également. Donc, côté programmation, les deux mains sur le clavier. Donc, Quantum Machine Learning, ça a été quand même un bon morceau de ton automne également.
Assez occupé comme automne.
Oui, quand même. Génial. Bien, merci beaucoup. D'ailleurs, si parmi vous, il y a des gens qui sont intéressés à vous joindre à l'équipe de programmation, donc à Sarah et au reste de l'équipe, on a un poste en programmation quantique qui est ouvert actuellement et on va mettre le lien vers l'offre d'emploi qui est sur le site web dans le chat. Donc, vous pouvez y avoir accès dès maintenant. Sur ce, avant de vous quitter, petite dernière annonce à faire, en fait. Surveillez vos infolettres, surveillez les différentes plateformes de l'Institut Quantique au courant des prochaines semaines. On a un projet d'animation vidéo qui vont vulgariser en fait l'informatique quantique qui vont sortir. Donc, restez à l'affût. Ça va être, enfin, on a très, très hâte de vous les présenter. Donc, ça va être une belle nouveauté qui s'en vient donc très, très bientôt. Et sur ce, j'aimerais remercier évidemment tous les panélistes qui ont participé ce matin à la présentation donc, de cette deuxième édition des Portes ouvertes de l'espace IBM Quantique de l'IQ. J'aimerais également remercier évidemment plusieurs personnes qui ont travaillé dans l'ombre, donc toute l'équipe de direction ici à l'Institut Quantique, l'équipe de programmation et tous les gens avec qui on travaille au quotidien. J'aimerais également remercier la compagnie Athénao, la compagnie de traduction qui vous a accompagné autant en français qu'en anglais vers l'autre langue ce matin. Merci à nos panélistes et à nos conférenciers là, donc de IBM, Lockheed Martin, CMC Microsystèmes, Statistique Canada. Merci à tous les gens de l'IQ également, là, donc Stéphanos, Aiki, Sarah. Et bon, on avait dit qu'on nommerait pas de nom pour les gens qui ont participé à confectionner l'horaire de ce matin quand je faisais le brainstorm avec Tom Mala la semaine passée. Mais je tiens à souligner son nom, même si on avait décidé de ne pas le faire. Donc, Tom qui a travaillé encore là cette année à la programmation de la matinée, à la technique qui est juste à côté de moi ici et qui, depuis tantôt, me fait des babayes quand il faut, puis s'assure que toute la mise en onde de la matinée se fait convenablement. Donc, Tom, merci beaucoup pour l'orchestration. Et évidemment, point de vue financier, j'aimerais remercier le ministère de l'Économie et de l'Innovation, sans qui, sans le financement de qui, il serait impossible d'avoir l'espace IBMQ ici à l'IQ. Donc, merci beaucoup pour votre support financier. Et sur ce, écoutez, je vous dis à la prochaine, à l'an prochain pour la 3e édition des Portes ouvertes de l'espace IBM Quantique. Bon appétit tout le monde.